It's October 28th, 24 hours before the event scientists have been waiting for and dreading. Right now, 3i Atlas is hidden behind the Sun, completely invisible to every telescope on Earth. For the first time since its discovery, there are no active observations, no confirmed readings, no visual tracking. The world's most unusual interstellar object has slipped into a total blackout. At 11:07 UTC tomorrow, October 29th, it reaches Perihelion, its closest approach to the Sun, the moment that determines everything. If this object behaves like a normal comet, it will brighten, flare, maybe fragment. But if it does anything else, any non-gravitational drift, any course correction, any asymmetric emission, the implications will reach far beyond astronomy. For the next 24 hours, data goes dark. No one knows what's happening behind that light. NASA remains silent. ESA's last transmission ended days ago, and even independent observatories have gone quiet. What happens now is unseen, unmeasured, and possibly unprecedented. When the blackout ends, we'll know whether 3i Atlas is just another piece of cosmic debris, or something that forces us to rewrite what we thought we knew about nature itself. The countdown has begun. For months, telescopes across the planet have been tracking a silent traveller, a dark object on a shallow, almost unnervingly perfect path across the ecliptic, 3i Atlas, and then, in the final days of October, it simply vanished. Solar conjunction. It's the one moment every astronomer dreads, when an object passes directly behind the Sun from Earth's perspective, becoming invisible to all optical instruments. The glare of our star overwhelms every sensor, every camera, every eye. For 3i Atlas, that blackout began 5 days ago, around October 23rd. Since then, every image, every data stream has gone silent. In normal cases, this isn't a problem. Comets disappear behind the Sun all the time. They vanish for a few days, emerge again, and resume their journey. But this isn't a normal case. This is the closest any confirmed interstellar object has ever come to our star, and the first to do so while carrying a trail of unexplained data. The last confirmed observation before blackout came from ESA's solar orbiter and a pair of ground-based telescopes in Chile. They reported something strange, a shift in brightness that didn't match the expected solar heating curve. Normally, as a comet nears the Sun, its albedo, its reflectivity, increases sharply due to gas and dust release. But 3i Atlas dimmed, slightly but unmistakably. That's not supposed to happen. If the object were fragmenting, it should brighten. If it were venting volatile material, its coma should expand, not contract. The last few images showed the coma narrowing, its shape tightening into a faint line aligned almost perfectly along the ecliptic. It looked less like a melting comet and more like a controlled trajectory. Behind the Sun, we can't verify anything. Radio silence, no optical access. Radar attempts from Goldstone failed, too much interference. Even the Parker Solar Probe, positioned for potential plasma readings, has not yet released any data. NASA's official statement came 3 days ago. No new visual confirmation of 3i Atlas during conjunction. That's all. To the public, it's a temporary pause. To researchers, it's a rare and critical blind spot. Because this blackout coincides precisely with Perihelion, the moment of maximum solar influence when any anomalous acceleration, outgassing or maneuver would occur. If something extraordinary happens, it's happening right now, unseen. A few independent astronomers have pointed out a strange coincidence. The timing of this conjunction window is nearly identical to the one experienced by Oumuamua in 2017, when it too was briefly unobservable during its critical trajectory shift. The difference? Oumuamua was already leaving the inner solar system by then. 3i Atlas is approaching its moment of truth. During these hidden hours, any change in momentum, any subtle deviation in vector, will go unnoticed until early November, when ground-based telescopes regain visibility. And that's where tension rises, because even a shift of a few arc-seconds, just a few kilometers per second in velocity, could signal something unnatural. The International Asteroid Warning Network has been monitoring the object, even though there's no impact risk. That in itself is unusual. IAWN normally focuses only on objects with Earth-crossing trajectories. 3i Atlas doesn't come anywhere near our planet. Yet it remains under special observation. No explanation given. Some suggest it's simple caution, an abundance of vigilance after Oumuamua. Others see it differently. The precision of its path, the improbable alignment with the ecliptic, and its low inclination entry all raise questions. The last calculated orbital parameters place it at an inclination of just 0.7 degrees relative to Earth's plane. For a visitor from interstellar space, that's statistically improbable, less than 1 in 100,000 based on galactic motion models. So as it vanished behind the Sun, astronomers weren't just watching a comet disappear, they were watching a mystery go dark. When it re-emerges, we'll compare its pre- and post-perihelion trajectory. If it comes out exactly where models predict, physics holds. If it doesn't, if even a minor drift appears, that deviation could become the most important data point in modern astronomy. But for now, there's only silence, an object from beyond the stars crossing behind our Sun, unseen, untouchable, unreachable. And when it comes back into view, the world may not see the same object that went in. For most of human history, a comet's passage near the Sun was something to fear. It meant omens, disruption, the sudden appearance of a light that came from nowhere and vanished without explanation. But what is happening right now, as 3i Atlas passes through the most critical 24-hour window of its orbit, is more than a historical echo. It's a direct confrontation with our ability to understand what we're seeing and what we can't. October 29th, the date that astronomers have been marking, modelling and quietly debating for months. This is the day when 3i Atlas reaches Perihelion, its closest approach to the Sun. Based on its calculated trajectory, that point lies at roughly 0.47 astronomical units, a little inside the orbit of Venus. At that distance, solar radiation is more than 4 times stronger than what we experience on Earth. For a typical comet, this would trigger an intense outburst of sublimation, the release of frozen gases that have been locked inside for eons. But 3i Atlas isn't behaving like a typical comet. Spectroscopic readings from before the blackout show almost no evidence of water vapour. The traditional marker of cometary activity, the 2.7 micron emission line of water, is absent. Instead, sensors from the European Southern Observatory picked up something few had expected: strong nickel emissions, specifically nickel tetracarbonyl and metallic nickel gas. This alone changes everything. Nickel tetracarbonyl is a compound that shouldn't survive near the Sun. It breaks down under high heat. For it to appear consistently in 3i Atlas's tail means either a replenishing mechanism or a fundamentally different chemistry. The ratios between nickel and iron in its spectrum don't match any natural cometary record. Even comets like 2I/Borisov, the only other confirmed interstellar body to show heavy metal emissions, had them in small, unstable amounts. In 3i Atlas, nickel dominates. Why does that matter? Because nickel is both heavy and non-volatile. It doesn't boil off easily. For such material to leave a body in measurable quantities, it would require localized heating or controlled venting. The data implies jets or flares concentrated along specific vectors, one of them remarkably pointed almost directly toward the Sun. That's the opposite of what we expect. During normal sublimation, the gas jet pushes away from the Sun, forming a tail that extends outward. But here, several instruments, including early September readings from the Lowell Observatory, suggested a faint anti-tail, a stream extending toward the Sun itself. It's as if something was directing emissions sunward, countering the pressure of solar wind rather than being swept by it. And now, as the object passes through perihelion unseen, this behaviour becomes the focus of every model. Because the physics of this moment will determine which narrative survives. Is 3i Atlas a bizarre interstellar rock with unusual chemistry, or is it something capable of active regulation, perhaps even manoeuvring? Let's walk through what this crossing actually looks like from an orbital standpoint. Imagine the Sun at the centre. Around it, the 8 planets trace their elliptical paths, mostly confined to a single thin plane called the Ecliptic. 3i Atlas approaches along almost exactly that plane, its inclination less than 1 degree. For an interstellar object, one not born in our solar system, that's extraordinary. Statistically, such low inclination entries are rare because the galactic random velocities that bring these objects toward us should produce a wide range of approach angles. Yet this one aligns with the same geometric plane that governs Earth, Venus and Mars. At perihelion, 3i Atlas's velocity peaks around 74 km per second, about 165,000 miles per hour. The gravitational pull of the Sun accelerates it to that speed, bending its path in a sharp curve before releasing it back outward. But here's where things could diverge. If there's any additional acceleration not accounted for by gravity, even a fraction of a meter per second squared, the outgoing trajectory will shift measurably. That's how we detected anomalies in Oumuamua, and it's how we'll test 3i Atlas when it re-emerges. For now though, it's in a zone of pure speculation. No telescope can see it. The sun's glare is absolute. Only space-based instruments could, in theory, observe it, but none have reported data. The Parker Solar Probe is too deep inside its own radiation shield to make visual contact. The Solar and Heliospheric Observatory, SOHO, has cameras that could potentially capture a faint silhouette, but as of this hour, no such detection has been announced. The absence of data doesn't mean the absence of activity. It means we're flying blind during the most critical moment of the object's journey, and that's where tension builds. Because when an anomaly disappears at the very moment its behaviour could reveal something decisive, history remembers. We've seen this pattern before. When Oumuamua passed through its perihelion in September 2017, it too was obscured by solar glare. Only weeks later, after it had passed, did observers notice its trajectory no longer matched gravitational predictions. The extra acceleration was tiny, less than 1/10,000th of what sunlight alone could cause, but it was real. It couldn't be explained by standard models. The debate that followed has never ended. Now, we're at that same threshold, but with higher stakes. 3i Atlas is larger, denser, and on a far lower inclination than Oumuamua. If it shows a similar non-gravitational effect after emerging from conjunction, it will be much harder to dismiss as coincidence or simple outgassing. Astronomers have mapped 3 possible scenarios for what's happening during this hidden crossing. Scenario 1, the natural outburst. As it nears perihelion, internal volatiles react to solar heat, causing jets to erupt unpredictably. The object brightens, fragments slightly, then stabilizes as it leaves the sun's immediate influence. Scenario 2, organized fragmentation. The body breaks into several controlled pieces, not chaotic debris, but distinct co-orbiting components that maintain relative spacing. This has been seen before in artificial bodies, like defunct satellites, under controlled drift. Scenario 3, an intentional course change. This is the most controversial possibility. It implies that 3i Atlas uses solar heating, gas emissions, or other means to alter its outbound vector in a deliberate manner. If such an acceleration occurs, it would manifest as a measurable deviation in the expected post-perihelion trajectory by mid-November, when new tracking resumes. For now, all we can do is wait. But even waiting has become political. ESA has confirmed it will release new tracking data the moment visibility returns. NASA, by contrast, has not commented on any post-perihelion observation plan. Several research teams claim to have requested imaging time from the Mars Reconnaissance Orbiter, MRO, which could theoretically capture 3i Atlas near its closest approach, but no confirmation of such images has been made public. Some suspect they exist. The timing and alignment were ideal, but remain classified pending review. Meanwhile, the International Asteroid Warning Network, which normally reports small body impact probabilities, continues to issue quiet updates on orbital solutions. In their latest bulletin, they describe 3i Atlas as object of sustained interest. That phrase, within this context, is unusual. It implies continued coordination across global observatories, even though, officially, no threat exists. In the scientific community, reactions are split. One group insists this is simply a comet with unusual chemistry, perhaps formed in a nickel-rich region of another star system. Another group, including Harvard's Avi Loeb, argues that the consistent nickel emissions, the anti-tail orientation, and the synchronized timing of perihelion blackout point towards something more structured, possibly engineered. Loeb has called this an experiment in nature, but critics accuse him of overreach. Still, the timing's impossible to ignore. The object reaches its perihelion precisely while hidden from every major telescope on Earth. For all practical purposes, it could do anything right now, and no one would know until it emerges. In the absence of light, speculation becomes data. Forums, research threads, and independent astronomers trade calculations and simulated trajectories. Some estimate that if 3i Atlas were to alter its velocity by even 0.001% during this crossing, that would result in a positional shift of tens of thousands of kilometers by December, easily detectable by JWST. Others counter that such a change could still be natural, the result of uneven mass loss or outgassing jets. But the underlying issue remains. We're entering a moment when the line between natural and intentional is thinner than ever. Right now, the Sun is acting as a curtain. Behind it, an object from another star system is undergoing the most critical moment of its orbit. It's bombarded by radiation, heated to hundreds of degrees, subjected to gravitational and magnetic forces beyond any laboratory's reach. And somewhere in that invisible glare, something is happening, whether it's geological, chemical, or something else entirely. When it reappears, the solar wind will have sculpted whatever remains. It might emerge brighter, with a growing coma like any normal comet. Or it could emerge dimmer, stripped, reshaped, or in fragments that seem too symmetrical to be random. In the next few days, astronomers will be waiting at observatories from La Silla to Mauna Kea, from the James Webb Space Telescope's infrared detectors to Japan's Subaru Array, scanning the region of sky just west of the Sun. The instant it clears the glare, tracking begins anew. The first coordinates, the first velocity measurements, the first brightness curve. These will determine whether 3i Atlas was just another frozen relic, or something that moved with purpose. The hidden crossing isn't just about what's happening behind the Sun. It's about what we'll discover when the light returns, and when it does, the numbers will either settle the debate or ignite something far bigger. When the first spectral data from 3i Atlas arrived, it didn't look like a comet. It looked like something else, something metallic, heavy, and deeply wrong for an interstellar visitor. Astronomers have seen many kinds of chemical compositions in small bodies, carbon-rich, silicate-based, ice-dominant, even organic-heavy, but never one that shone with the signature of nickel, pure, unblended, and persistent. It began in late August. Observatories across Europe and South America turned their spectrometers toward the faint, fast-moving point that had entered our solar system at a shallow inclination. As the readings came in, the usual lines of hydrogen, oxygen, and carbon dioxide were missing. Instead, emission peaks around 340 and 510 nanometers appeared, frequencies associated with nickel and its rare gaseous compounds. At first, the data was dismissed as noise, a calibration issue. But then it appeared again, in independent observations from the European Southern Observatory and the Calar Alto Observatory in Spain. The signal was real. To understand how unusual that is, we have to look at what makes comets glow. When sunlight hits a comet, it vaporizes the ices on its surface, usually water, carbon monoxide, or methane. The escaping gas carries dust and metals with it, producing bright spectral lines in the visible and infrared range. Most comets are dominated by water vapor. Even the driest still contain trace H2O emissions, but 3i Atlas does not. Its waterline sits at background level, effectively zero. Instead, it releases nickel. And not just nickel tetracarbonyl, a compound that exists only under specific conditions of pressure and temperature. In laboratory settings, it forms when nickel combines with carbon monoxide gas, a reaction that requires both high metallic content and precise thermal stability. On Earth, it's used in industrial metallurgy for refining ultra-pure nickel. In space, it shouldn't exist. The vacuum, radiation, and temperature fluctuations would destroy it. Yet here it is, forming a distinct sustained spectral signature around an object travelling 70 kilometers per second through interplanetary space. This was the first sign that something about 3i Atlas didn't fit the natural template. At first, researchers proposed a metallic core exposure model. Perhaps the comet had lost its outer ices during eons in interstellar space, leaving behind a dense nickel-iron heart. That could explain the emissions, sunlight heating the bare metal causing sublimation of trace carbon compounds. But this raised a new problem. A body composed primarily of nickel would be extraordinarily dense. Its gravitational behaviour, if purely inertial, would differ from what telescopes measured. Yet the orbital solutions remained consistent with a much lighter, porous object. That mismatch, mass versus reflectivity, remains one of the deepest puzzles. Let's look at the numbers. Based on brightness alone, 3i Atlas appears roughly 1.2 kilometers across, comparable to a mid-sized asteroid. But when scientists used its acceleration data from August and September to estimate non-gravitational forces, they found values nearly 10 times lower than expected for a comet of that size. In simple terms, it doesn't behave as if it's made of light material. It moves as though it's heavy, much heavier than its visible surface area would suggest. Some estimate its density exceeds 8 grams per cubic centimetre, approaching that of solid nickel itself. So here's the paradox. 3i Atlas behaves like a massive metallic body, yet emits chemical signatures of refined nickel compounds, all while showing almost no trace of common volatiles. The combination is unique. Even Oumuamua, with its flat, tumbling shape and non-gravitational acceleration, never displayed anything like this. The scientific community split quickly. Some researchers, especially those working with ESA's spectral data, argue that the nickel lines could come from photochemical reactions in a carbon-rich crust. Others, including a team from the University of A Coruña, insist it's entirely natural, a relic from a planetary core ejected during a stellar explosion. But not everyone agrees. Harvard astrophysicist Avi Loeb, who had already drawn global attention for proposing that Oumuamua might have been artificial, saw a pattern. He pointed out that nickel tetracarbonyl isn't just unusual, it's functional. On Earth, it's used in processes where heat is deliberately controlled. In vacuum systems, it's a sign of refinement, not randomness. Loeb suggested that such emissions could indicate localized energy manipulation, a polite way of saying possibly artificial regulation. Critics dismissed it as speculation, yet the data kept coming. By mid-September, several instruments recorded something even stranger. The nickel emission wasn't random across the surface. It appeared concentrated along one hemisphere, a fixed direction relative to the object's rotation, the same side that faced the Sun. This pattern remained stable over weeks, despite the object's high speed and changing solar angle. Normally, cometary emissions vary as the nucleus rotates, but here the pattern was steady, almost locked. One explanation is that 3i Atlas rotates extremely slowly, perhaps once every several days, so its venting remains fixed relative to sunlight. But models of its light curve suggest otherwise. It flickers faintly every 9 hours, consistent with a tumbling, irregular body. That should randomize emission points. It doesn't. So either the object has some internal mechanism regulating which side releases material, or we're missing something about its structure. Could it have deep fissures channeling gas through narrow vents that only open under specific conditions? Could it possess a layered crust that insulates certain materials until sunlight penetrates at just the right angle? Both are possibilities, but they don't explain the precise stability of the nickel jets. Then came the radar anomaly. In late September, radar echo experiments from the Goldstone Solar System radar attempted to detect reflections from 3i Atlas. The results were inconclusive, except for one odd feature. The reflected signal had an unusually high radar albedo, suggesting a smooth metallic surface area larger than expected. For comparison, natural comets typically have radar albedos of around 0.04, meaning they reflect only about 4% of radar energy. 3i Atlas returned an estimated 0.3. That's nearly an order of magnitude higher, consistent with metal, not rock or ice. Put all this together, and the picture becomes difficult to ignore. A massive object, heavier than expected, a composition dominated by nickel compounds, a stable sun-facing emission pattern, and a radar profile hinting at smooth metallic surfaces. These are not the hallmarks of a normal comet. Still, the natural explanations persist. Some astrophysicists argue that interstellar objects might represent fragments of exotic planetary cores formed in environments vastly different from our own, worlds orbiting metal-rich stars where such compounds could be common. Others counter that even if that were true, the stability and uniformity of the nickel emissions still require an active process. The argument isn't just academic. If 3i Atlas turns out to be natural, it expands our understanding of how diverse interstellar material can be. But if it isn't, if the nickel lines represent engineered behaviour, then this object becomes the first empirical evidence of technology beyond our solar system. Right now, as it hides behind the Sun, those emissions may have intensified, weakened, or even ceased. When the object re-emerges in early November, telescopes will measure whether the nickel spectral lines remain consistent. If they've shifted in frequency or disappeared entirely, it could indicate a structural change during perihelion, fragmentation, melting, or some kind of transformation. But if they return, identical and stable, the case for something organised will grow exponentially stronger. NASA has not released any post-conjunction spectral data yet. The James Webb Space Telescope is scheduled to observe the object again around December 19th, when it will be far enough from the Sun to capture infrared detail. Those readings will determine whether the nickel compounds persist and whether the emissions are isotropic or directional. ESA's preliminary models predict a gradual decline in nickel intensity as the object cools. But some independent simulations, including one presented at the European Planetary Science Congress, suggest that if nickel tetracarbonyl formation is being thermally regulated, in other words, if it's part of a feedback process, then perihelion could actually increase its production for a short period, leading to an unexpected brightening once visibility resumes. If that happens, it won't just be a chemical curiosity, it will be a signal, not of communication, but of control. A sign that 3i Atlas responds to its environment in a way no random rock should. For now, every model remains suspended in uncertainty. The last recorded emission intensity, taken on October 21st, stood at a level nearly 14 times higher than any comparable comet. Since then, silence. The next reading, when it comes, will decide which side of the argument history remembers. Because if the nickel signal continues, unwavering, directional, and defiant of solar chaos, then this is no longer a mystery of chemistry. It's a question of intent. A comet's tail is one of the simplest and most predictable structures in astronomy. It always points away from the Sun, not because of motion, but because of pressure. Solar radiation and charged particles stream outward, sweeping dust and gas behind the object in a straight line opposite the Sun's position. It's basic physics. Every comet, from Halley to Borisov, obeys it without exception. But 3i Atlas doesn't. In the images taken between September 15th and October 21st, the final days before solar conjunction, astronomers noticed something disorienting. The tail wasn't pointing away from the Sun, it was pointing toward it, a faint luminous streak extending in the direction of the light itself rather than away from it. They called it an anti-tail. In theory, anti-tails can occur under specific optical conditions, when Earth happens to cross the plane of a comet's orbit, making its dust trail appear reversed due to perspective. But this wasn't that. The orbital geometry didn't fit. Earth was several degrees above the object's ecliptic plane. The alignment was off. Even accounting for parallax, the tail's orientation defied standard scattering models. This was not a trick of perspective, it was physical. When the European Space Agency's solar orbiter captured a distant glimpse of the object on October 9th, the anomaly became undeniable. The dust emission vector was sunward by roughly 17 degrees and remained steady for nearly a week. It wasn't flickering or rotating like a misaligned jet. It was stable, directional, and faintly luminous in wavelengths corresponding to metallic dust. In simpler terms, something was pushing material toward the Sun. To understand how extraordinary that is, we have to recall how comet tails form. A normal comet sublimates volatile ice as it heats, releasing gas and fine particles. Solar wind pressure, a stream of protons and electrons, exerts force on that material, pushing it outward. Even the weakest radiation field is enough to dominate. A single square meter of dust feels a steady outward push, hundreds of times stronger than the object's gravity can hold. For 3i Atlas to produce a tail facing the opposite direction, an inward force must be acting on its emissions, strong enough to overcome the solar wind's push. What could cause that? There are three possibilities, none of them simple. The first is electrostatic attraction. If 3i Atlas is heavily charged, perhaps from continuous interaction with solar plasma, it might pull ionized dust back toward itself, giving the illusion of a reversed tail. But the distances involved make that unlikely. The tail extended tens of thousands of kilometers, far beyond the reach of any localized electric field. The second is magnetic confinement. If the object possesses a magnetic field, either remnant or induced, it could redirect charged particles along field lines looping toward the Sun. Yet that would require a field strength comparable to small planets. For a body roughly 1 kilometer across, that's implausible unless it contains ferromagnetic material and active current flows. The third, and most controversial thus, is controlled emission. In this model, 3i Atlas releases material along specific vectors, perhaps from jets or vents aligned toward the Sun. The result, a stream of nickel and dust travelling counter to solar wind, forming what looks like a sunward tail. It's not being pushed inward, it's being fired inward. That idea unsettled the community. not because it implies technology, but because it breaks the rules of natural physics as we understand them. There is no known mechanism by which an inert, non-rotating object emits mass consistently in one direction against solar pressure. The energy cost alone would be staggering, yet the data shows stability, not chaos. When ESA published its partial trajectory data on October 12th, the tail orientation coincided with a minor deviation in the object's acceleration. Nothing conclusive, just a 0.0003 meters per second squared variance relative to the predicted model. It could be nothing, it could be something. For comparison, Oumuamua's unexplained acceleration was roughly 0.0005 meters per second squared. Both magnitudes are too small to notice without precision tracking, yet large enough to indicate non-gravitational forces. If 3I Atlas really did eject material sunward, the recoil effect would act as thrust, a tiny continuous push altering its orbit. The direction of that thrust would matter enormously. Pushing material toward the sun would push the object itself outward, slightly expanding its trajectory. It's counterintuitive but measurable. By early November, when new tracking resumes, astronomers will know whether its path diverges even slightly from the gravitational solution. If it does, that's direct proof of active acceleration. The problem is, we don't know what's happening right now. We can't see it. The object is still hidden behind the sun, possibly venting, fragmenting, or doing nothing at all. The anti-tail might have faded, strengthened, or inverted again. No one will know until the first post-conjunction frames arrive, likely from the Las Cumbres Observatory Network or ESA's solar orbiter, depending on timing. Meanwhile, theories multiply. Some propose that the anti-tail is an illusion caused by complex forward scattering. In this view, metallic dust, denser and more reflective than typical silicate grains, could scatter sunlight forward rather than backward, making the illuminated side appear to extend toward the sun. But for this to work, the dust particles would need to be microscopically precise in size and composition, a level of uniformity rarely seen in nature. Others point to a more radical idea, a propulsion-like effect. They note that 3I Atlas's nickel emissions, already known to be directional, align almost perfectly with the anti-tail axis. If those emissions are ejecting metallic vapor sunward, the resulting momentum could subtly alter its course. Essentially, what looks like a tail might be exhaust. This interpretation fits too neatly for some scientists to accept, but history has seen stranger coincidences. In 2020, a small near-Earth object designated 2020 SO was later confirmed to be part of a Centaur rocket stage, a man-made artifact mistaken for an asteroid. Its reflective coating produced unexpected brightness curves, confusing observers until the orbit told the truth. Now with 3I Atlas, we're facing a similar ambiguity, only magnified across interstellar scales. If this were natural, it would expand our understanding of how metallic comets interact with stellar environments. If it isn't, we're witnessing something unprecedented, a demonstration of directed emission across millions of kilometers. But even beyond the physical explanation, the anti-tail poses a deeper, more philosophical question. What would make an object release matter toward the very source of destruction? The sun, in this case, is both a threat and an opportunity. Its radiation could be harnessed for acceleration, the same principle behind light sails. By ejecting mass sunward, a body could exploit solar pressure for maneuvering. It's a concept known in engineering circles as differential solar thrust, once proposed for autonomous probes. The mechanics match almost perfectly. That's what troubles many researchers. The anti-tail doesn't just look unnatural, it behaves like a system designed for controlled navigation. Still, even the most cautious voices admit we need more data. When 3I Atlas emerges, astronomers will measure three key parameters: the orientation of its dust emission vector relative to solar direction, the spectral ratio of nickel to iron, which determines whether metallic vaporization continues, the phase curve of polarization, revealing the alignment of light across its surface. If those three metrics remain consistent with pre-conjunction readings, the anti-tail can no longer be dismissed as an illusion. It will represent a persistent directional phenomenon, one that requires energy, organization, and intent. And yet, there's one more detail few have noticed. On October 19th, just before blackout, NASA's Solar Dynamics Observatory recorded a faint transient near the solar limb, a brief brightening consistent with dust impact or localized plasma interference. The coordinates match within error range to 3i Atlas's predicted ingress point. Some suggest it could have been a dust trail interacting with solar wind. Others whisper it was something else, a reaction, not an accident. NASA made no comment. The image remains archived, unexplained. So here we are, an object with a tail that points the wrong way, a composition that doesn't match any comet ever observed, and a blackout perfectly timed to its most critical orbital phase. The anti-tail might be nothing. It might be everything. If, when the light returns, that sunward jet remains, unwavering, bright and stable, then the story of 3i Atlas changes forever. Because a comet's tail always tells the truth about what drives it, and this one may be telling us that something, somewhere inside that distant traveller, is awake. Light is not just brightness, it's structure. When it reflects off a surface, it carries information about what it touched, the texture, composition, and even the geometry of that material. Astronomers call this polarization, the measure of how light waves align after reflection. It's one of the most subtle yet powerful diagnostic tools in planetary science. And with 3i Atlas, polarization has revealed something that shouldn't exist. The first polarization readings came in mid-September, when the object was still easily observable from Earth-based telescopes. Early data from the Calais Observatory in France and the Rojan National Astronomical Observatory in Bulgaria indicated an anomaly so pronounced that the teams initially assumed instrumental error. The object's reflected light was negatively polarized, not slightly, but extremely. To grasp the meaning of that, think of polarization as a fingerprint. Normal comets, with their dusty, uneven surfaces, polarize sunlight in a predictable way. The electric field of light waves becomes partially aligned in one direction, usually positive polarization. Negative polarization, on the other hand, occurs only under specific conditions, typically when light scatters off extremely smooth or fine-grained particles. Even then, the magnitude is small. But 3i Atlas showed an angle of negative polarization that exceeded negative 2.6%, double that of any natural comet on record. In short, the object reflects light as if it were covered not in dust, but in something fine, metallic, and organized. Astronomers immediately began comparing the data to known materials. Simulations using polarized light models for silicates, ices, carbon compounds, and even iron oxides all failed to reproduce the curve. The only match came from synthetic surfaces, specifically microstructured nickel lattices and electroplated metal foils. In laboratory tests, such materials produce the same kind of negative polarization when illuminated at shallow phase angles. That alone wouldn't mean much if not for one crucial detail. The effect remained stable. Normally, as a comet rotates, its polarization angle shifts. The light scatters differently as the surface presents new textures to the sun. But throughout several observation nights, September 18th, 21st and 24th, the readings remained almost identical. Whatever covered 3i Atlas, it wasn't random. It was consistent across at least half its surface, suggesting either a uniform layer or something manufactured to maintain optical coherence. Some observers wondered if this could be the result of melted or sintered metals. As the comet approached the sun, high temperatures could fuse metallic grains into a smoother crust, reducing polarization variability. Yet temperature models show the surface shouldn't have reached that point. At its distance then, about 0.6 astronomical units, the peak temperature would be roughly 600 Kelvin, far below nickel's melting point of 1728 Kelvin. No natural sintering would occur, so what's left? A metallic film, perhaps a residue from outgassed compounds, or something else entirely. Let's look at how deep this mystery runs. In late September, a team from the Arecibo Observatory attempted radar polarimetric measurements before conjunction. Radar waves, like visible light, can be polarized, and their echoes provide information about surface structure. The result, a reflection ratio inconsistent with random terrain. Instead of the expected diffuse scattering, the echoes showed coherent backscatter, as though bouncing off aligned panels or facets. Arecibo's team leader, Dr. Elise Ramirez, summarized it bluntly. The surface behaves like it has order. Order, in this context, doesn't mean deliberate design. It could mean crystalline regularity or a highly anisotropic mineral texture. but combined with the optical polarization data, it paints a picture that's difficult to ignore. 3I Atlas is reflecting sunlight and radar in a way that suggests smoothness, uniformity and precision on a scale no natural comet has ever exhibited. Let's break down what negative polarization implies in detail. When light hits a rough, dusty surface, it scatters chaotically. The resulting polarization tends to align parallel to the scattering plane. That's positive polarization. But when it reflects off tiny, uniformly sized particles smaller than the wavelength of light, the scattered waves interfere destructively in most directions and constructively in one. This reverses the polarization direction, creating a negative signature. It's an optical effect called coherent backscatter. Now, comets occasionally show slight negative polarization near zero-phase angles, essentially when viewed head-on relative to the Sun. But 3I Atlas's curve extended across phase angles of 20 to 50 degrees, where the effect should vanish. That persistence means the surface particles are not random. They are arranged, whether naturally or artificially, to maintain coherent reflection across a wide angular range. Imagine a vast sheet of microscopic mirrors, each angled just enough to redirect sunlight in unison. That's what the data implies. This phenomenon also connects directly to its other anomalies. Nickel, as noted in Chapter 3, dominates its spectrum. Polished nickel surfaces are highly reflective and exhibit negative polarization in the same range observed here. If the object's outer layer has become coated in nickel vapor that condensed evenly, it could theoretically create a reflective shell. But again, how? Nickel vaporization requires controlled temperature gradients, not chaotic sublimation. The result feels engineered, but science hesitates to use that word. ESA's official explanation, published briefly in its October 14th bulletin, proposed self-laminating crustal development. In plain terms, the idea is that nickel compounds vented from the surface could recondense nearby, layering the object with a thin metallic film as it rotated. The process would be slow, requiring weeks of continuous outgassing. That could explain the uniform polarization and the fixed emission patterns. Yet that model demands stability, and 3I Atlas's orbit doesn't allow much of it. Travelling at tens of kilometers per second through turbulent solar wind, any fine dust would be stripped away. For lamination to persist, it must be constantly renewed, implying a feedback process. In other words, the object maintains itself. The comparison many scientists avoid is spacecraft thermal coating. Certain probes use nickel chromium or gold films to regulate heat, reflecting solar radiation at controlled wavelengths. These surfaces produce strong negative polarization under similar conditions. The resemblance is uncomfortable. Skeptics argue this is anthropocentric bias. We see patterns of technology because we're used to finding order in chaos. They suggest a more natural origin: interstellar erosion. Over millions of years, high-velocity dust impacts could have polished its surface, creating an optically smooth crust. That's plausible, until you recall that the object emits nickel gas. For such material to survive erosion and still vent chemically active metals, its crust can't be ancient, it's fresh, it's changing in real time. Then there's the issue of temperature variation. Observations in near-infrared bands showed almost no thermal gradient across the visible surface. Normally, a comet shows hot and cold regions as it spins. 3I Atlas doesn't. It radiates heat evenly as if covered by a uniform conductor. The implication? It's distributing solar energy efficiently. This is not how natural bodies behave. The deeper scientists dig, the more every dataset folds into the same shape: coherence, uniformity, balance. The very qualities randomness should erase. By October 21st, the final day before optical blackout, the polarization anomaly peaked. The reflected light curve flattened, its amplitude nearly zero. That means the brightness no longer fluctuated with rotation, as though the entire object had become homogeneously reflective. Then, the data ended. If the trend continued, 3I Atlas may now be passing Perihelion as a fully metallic reflector, either encased in self-condensed nickel or something else entirely. When it emerges, one of two things will be clear. Either the polarization collapses, meaning the crust fragmented and the reflective layer burned away, or it persists, proving that the structure is stable under conditions that should destroy it. In December, the James Webb Space Telescope will test that question. Its near-infrared imager and slitless spectrograph, NIRISS, can measure polarization indirectly by analysing the distribution of reflected light intensity at different wavelengths. If the negative curve still exists, that will confirm the crust has survived perihelion intact, and if it has, we're no longer dealing with a transient comet. We're looking at a body designed, or evolved, to endure solar proximity. Whatever the truth, polarization is one of the most unforgiving metrics in astrophysics. It doesn't lie, it doesn't exaggerate, and it doesn't care what story we prefer. It only reveals how ordered light becomes after contact, and in this case, that order is whispering something we can't yet define. Somewhere behind the sun, a kilometre-wide object is crossing its brightest moment, wrapped in a shell that behaves like engineered metal, reflecting light in ways nature shouldn't allow. And when it comes back into view, the first glint of that reflection, its shape, its tone, its polarization, might be the closest thing to a signature we'll ever see. In every scientific investigation, there comes a point where numbers stop behaving. With 3i Atlas, that moment came when astronomers tried to calculate its mass. At first glance, this should have been simple. Measure its brightness, estimate its size, assume a typical density for a comet or asteroid, and the math tells you how much material it holds. But from the very beginning, the numbers refused to make sense. When the Pan-STARRS survey first catalogued 3i Atlas earlier this year, photometric analysis suggested a nucleus roughly 1.2 kilometers wide. That would normally imply a mass on the order of 10 to the power of 12 kilograms, a modest rock by cosmic standards. Yet orbital models didn't agree. The object's motion, its speed through interstellar space, and its subtle interactions with the solar wind all pointed to something far heavier. The initial discrepancy was small, less than a few percent. But as the months passed and more tracking data accumulated, that gap widened until it became impossible to ignore. The latest independent estimates, compiled just before conjunction, suggest a lower bound mass of 3 × 10 to the power of 13 kilograms. That's 30 times higher than the photometric model predicts. To put that into perspective, 3i Atlas behaves gravitationally like an object the size of Mount Everest, even though its visible cross-section is barely that of a city block. Something doesn't add up. This mismatch, now known as the mass discrepancy, has become one of the most debated aspects of 3i Atlas's behaviour. The question is simple. If it really is that massive, why doesn't it look like it? Where is the material hiding? Let's start with the basics. The observed brightness of a celestial body depends on its albedo, how much sunlight it reflects. A bright surface means a small object can appear large, while a dark surface can make a massive body seem tiny. For comets, typical albedos range from 0.03 to 0.06, as dark as coal dust. Even a slight error here can change mass estimates dramatically. But 3i Atlas's albedo isn't dark, it's bright. Polarization readings suggest reflectivity closer to 0.3, 50 times higher than average. That means it should appear larger than it is, not smaller. So the high mass can't be explained by reflection alone. The second variable is density. Comets are usually porous, with densities around 0.6 grams per cubic centimetre, essentially half the density of water. Asteroids range from 2 to 3 grams per cubic centimetre. Metal-rich bodies can reach 8 or even 9. If 3i Atlas is composed mostly of nickel, its density could fall at the upper extreme, but even assuming a solid metallic interior, the total mass should still fall below 10 to the power of 13 kilograms. Yet calculations show orbital perturbations consistent with an even greater value. How do we know? Because gravity leaves fingerprints. When 3i Atlas passed through the inner solar system, its trajectory was influenced by subtle, gravitational interactions with other bodies, primarily Mars and the Sun. Those deviations can be back-calculated to infer mass indirectly. In early October, a team from the Jet Propulsion Laboratory analysed its pre-perihelion acceleration vector and found that it responded less to solar wind pressure than expected. That means it has higher inertia and therefore higher mass. Here's where things turn strange. The same models that confirm its high mass also show that its cross-sectional area, the part of it exposed to solar wind, is unusually small relative to that mass. In other words, it's too heavy for its size and too stable for its shape. If 3i Atlas were a hollow shell, it would accelerate easily under radiation pressure. If it were porous, it would show large outgassing forces. Neither is happening. The object moves through the inner system like a bullet, dense, compact, and eerily unaffected by forces that should buffet it. That's when the radar data came in. On September 29th, the Goldstone Solar System radar managed to capture faint echoes from 3i Atlas, producing a rough shape model. The return suggested a body roughly elongated, 1.3 by 0.9 kilometers, with low radar roughness. But here's the anomaly. The radar brightness was far higher than expected for an object that size, almost an order of magnitude stronger. Combined with its motion, this implies either a highly metallic composition or internal reinforcement. ESA's engineers noticed another clue. The timing of radar echo fading hinted at multiple reflections, as if some of the signal was bouncing off internal structures before returning. Natural bodies don't do that, but cavities or stratified layers of differing density might. Imagine a hollow within the rock, not an empty void, but an organized, dense core surrounded by less dense material. That configuration could explain the mass anomaly. Concentrated mass at the center, reflective but compact. Still, not everyone agrees. Some argue that the data is too sparse for such conclusions. They point instead to non-gravitational modelling errors, the possibility that outgassing forces weren't properly subtracted, leading to miscalculated mass. But this doesn't hold either. There's almost no water or CO2 detected from 3i Atlas, meaning minimal gas thrust. The object simply isn't behaving like a sublimating comet. If the numbers are correct, it has a density nearly equal to solid nickel, 8.5 grams per cubic centimetre, and a mass-to-brightness ratio unseen in any interstellar visitor to date. That raises two unsettling possibilities. Possibility 1. 3i Atlas is the fragment of a planetary core from another star system. A solid metallic shard forged in extreme heat, stripped of its lighter elements, and wandering for millions of years. That would make it the densest naturally formed interstellar object ever discovered. Possibility 2. The mass is artificial. The second possibility emerges from how consistent the measurements have been. Normally, as comets approach perihelion, their apparent mass fluctuates due to outgassing and fragmentation. But 3i Atlas's inferred mass hasn't changed. Even as it accelerated toward the Sun, no measurable mass loss occurred. It's as if the object is actively maintaining its structural integrity. That could mean reinforcement, internal bracing, self-regulating composition, or simply material so strong that solar heating can't touch it. But it could also hint at a more deliberate explanation, that what we're seeing is not a random fragment, but a constructed mass, engineered for stability across interstellar flight. This theory gained traction after a peculiar discovery in the late September data, a faint modulation in radar echoes repeating every 44 seconds. Too weak to be called a signal, too regular to be ignored. Some dismissed it as instrumental noise. Others noted that 44 seconds corresponds closely to the estimated rotational period of 3i Atlas's secondary component, the faint fragment detected in early imaging. Coincidence? Possibly. But in a mission with so many coincidences, each one demands attention. A few independent researchers proposed that the mass anomaly might stem from internal density variation, perhaps a denser core surrounded by porous layers. That's reasonable. Many asteroids show such differentiation, yet the consistency of its spin and lack of tumbling contradict that idea. A differentiated body with uneven mass distribution usually wobbles. 3i Atlas does not. Its rotation is smooth, almost inertial. The balance is too perfect. When the Solar and Heliospheric Observatory tracked its trajectory prior to conjunction, it detected almost no precession, no slow drift in its spin axis. That kind of rotational stability is rare in natural objects, especially those under thermal stress. It's more typical of symmetrical engineered structures, or at least of something that was once part of one. Still, caution prevails. Scientists working within ESA's Planetary Defense Office emphasize that mass discrepancy doesn't automatically imply artificiality. It could mean composition we haven't encountered before, nickel silicides, ultra-dense alloys, or compressed mineral phases formed under supernova conditions. Such materials could explain the high density and metallic reflectivity without invoking deliberate design. Yet the implications remain enormous. If 3i Atlas truly possesses 30 times more mass than its visible surface area suggests, then its gravitational influence should slightly distort the orbits of nearby dust and plasma streams. Small, measurable shifts in background particles could betray its true mass once observations resume. Instruments like JWST's near-infrared spectrograph and the JUICE mission's onboard sensors might detect these deviations in November and December. There's also another, quieter implication. If the object is indeed that dense, it means it's holding together under stress that would pulverize any comet. At perihelion, the tidal forces and thermal gradients are immense. A typical icy nucleus would fracture. 3i Atlas, by contrast, might emerge unchanged, or even stronger, its reflective crust annealed by solar heat. This endurance could mark the turning point in how we classify interstellar visitors. No longer simply comets or asteroids, but something in between, or beyond both. Objects capable of surviving close solar passes, retaining metallic shells, and resisting mass loss might represent an entirely new category. And if even one of them shows signs of deliberate structure, we'll have to reconsider the boundary between physics and intention. As of now, the official mass figure remains uncertain. But behind that word lies the quiet admission that our equations no longer close neatly. There's weight here, literal and metaphorical, that doesn't belong. When 3i Atlas reappears in early November, astronomers will compare its predicted ephemeris to reality. If it's even slightly off track, if its path curves differently than the gravitational model anticipates, the data will tell us that its mass isn't distributed the way we think. That would confirm what many already suspect, that there's something hidden inside. For now, all we can do is wait for the light to return, for the radar to echo again, and for the numbers to settle. But in every calculation so far, the same pattern emerges. The math refuses to shrink. In whatever 3i Atlas is, it weighs more than it should. And somewhere, in that invisible gulf behind the sun, that impossible weight is moving. Steady, silent, and precise. Every orbit tells a story. Some spiral steeply through the solar system, tilted like thrown stones. Others slice in from the dark, crossing planetary paths at odd angles before vanishing again into interstellar night. But 3i Atlas doesn't move like that. It doesn't wander. It slides, quietly, perfectly, along the same plane that Earth, Venus, and Mars call home, the ecliptic. That in itself is almost impossible. Astronomers have a term for how tilted an orbit is relative to the solar system's flat plane: inclination. For a natural interstellar object, the expected inclination is random. Think of the galaxy as a vast cloud of moving debris. Stars, planets, and asteroids drift through it in all directions. When something escapes one star's gravity and happens to cross another's, the odds that it'll enter perfectly aligned with that second star's planetary plane are astronomically low. It's like tossing a dart from across a football field and hitting a blade of grass edge on. For context, Oumuamua entered at an inclination of about 123 degrees. 2I/Borisov came in at 44 degrees. 3i Atlas, 0.78 degrees, less than 1 degree, practically cut-planar with the Earth itself. This is what scientists are now calling the ecliptic precision anomaly. When the first orbital elements were published by the Minor Planet Center, the number looked like a typographical error. Interstellar trajectories are supposed to be chaotic, not geometrically elegant. Yet subsequent refinements confirmed it. 3i Atlas moves through our solar system as if it belongs here, as if it chose the path of least resistance, threading between planets like a needle through silk. Why does that matter? Because in celestial mechanics, alignment isn't just coincidence. It determines visibility, gravitational influence, and interaction potential. The fact that this object entered along a near-perfect ecliptic trajectory means it passes directly through regions of dense observational infrastructure, near-Earth orbit, Mars orbital corridor, and the inner heliosphere, where our probes constantly measure plasma conditions. It's as if it's moving through our most instrumented zone. That precision raises one unavoidable question. How did it get here like that? Let's break it down. If 3i Atlas were ejected from a distant star system, its velocity relative to the galactic plane would almost certainly impart some inclination. Even a tiny angular deviation at the point of ejection translates to vast differences after millions of years of drift. Simulations run by ESA's Orbital Dynamics Group show that, given random ejection vectors, fewer than 1 in 100,000 interstellar objects would approach the solar system with an inclination under 1 degree. That's not impossible, but it's rare enough to demand attention. Some researchers propose that 3I Atlas could have been deflected into its current path by gravitational interactions, perhaps a near miss with Jupiter or another unseen body. But back-propagated trajectory analysis undermines that idea. Even before entering the planetary region, its inclination was already minimal. The deflection didn't happen here. It was born with that alignment, so either we've witnessed an extraordinary cosmic coincidence, or this object's approach was somehow fine-tuned long before it crossed our neighbourhood. A few fringe researchers, and even a few quiet insiders, have whispered comparisons to gravitational threading. The concept refers to using stellar gravity fields to guide long-duration travel across interstellar space. If an object could subtly alter its course over time, via minimal propulsion or controlled mass ejection, it could drift along specific galactic current lines, using the geometry of star systems as stepping stones. It's an idea pulled from deep space propulsion studies, not from mainstream comet dynamics. And yet, when you plot 3I Atlas's entry vector backward, it intersects within less than a degree of the galactic midplane, precisely the region where such threads would be most stable. Coincidence? Maybe, but the coincidences keep stacking. Consider this. When an interstellar object enters the solar system, its orbital parameters, inclination, eccentricity, and argument of perihelion, are expected to scatter randomly. But 3I Atlas not only travels along the ecliptic, its perihelion, the point of closest approach to the Sun, occurs almost exactly at the same heliolongitude as Earth's position 1 month earlier. In simple terms, its path crosses the solar system's plane at the very place Earth recently was. The alignment is that precise. Now think about that geometrically. The Sun, Earth, and 3I Atlas's orbital plane form a near-perfect line separated by mere degrees of arc, a difference so small that if Earth had been slightly ahead or behind in its orbit, the object's apparent path in the sky would have intersected our planet's own trajectory, not close enough to threaten collision, but close enough to ensure maximum visibility, maximum observation. This is where some scientists began to whisper about intent, even if only metaphorically, because if you were going to design a flyby to be noticed, but not to impact, this is the path you would take. And yet, it's not just visibility. The ecliptic alignment also provides gravitational efficiency. By staying within the same plane as the planets, the object experiences predictable perturbations, enabling smoother navigation through the solar system's energy contours. Even a minimal change in course, say a deliberate adjustment made far away, could result in this near-perfect threading through our planetary orbits. Astronomers at the University of Arizona simulated several million random entries into the solar system. Only 2 out of 1.2 million produced a trajectory within 1 degree of the ecliptic and a perihelion near Venus's orbit. Statistically speaking, that's a 0.00017% chance. The natural explanation would be that we're simply observing the tail end of probability, that rare events, given enough time, will occur. The problem is that this isn't the only anomaly. The nickel emissions, the negative polarization, the anti-tail, the mass discrepancy. Each one is improbable. Together, they start to feel like design. Still, the cautious voices insist otherwise. One leading orbital dynamicist at ESA stated, "Every improbable event still has probability. Nature is allowed to surprise us. It doesn't mean intention. It means we haven't seen enough examples fair enough." But there's a subtlety here that even seasoned scientists admit feels uncanny. The object's rotational axis, inferred from brightness modulation, is also nearly perpendicular to the ecliptic. That means its poles point north and south relative to the solar system's plane, keeping its broadest reflective surface facing the Sun for maximum visibility during approach. Again, if this were an engineered reconnaissance object, that orientation would be ideal, but no one wants to say that aloud. Another complication, during its approach, 3I Atlas's position relative to the heliospheric current sheet the wavy magnetic boundary separating solar magnetic polarity regions has remained almost constant. It seems to be gliding along one side of that current sheet, rather than crossing it chaotically as most comets do. Maintaining that course requires precision. Some call it luck, others call it control. Either way, the geometry is exact. By late October, right before conjunction, its predicted outbound trajectory was calculated to pass within 0.002 astronomical units of Jupiter's orbital plane next March, close enough that the JUICE spacecraft will be able to observe it from millions of kilometers away. That timing, too, is uncanny. A European probe designed for Jupiter's moons, now perfectly positioned to glimpse the first interstellar object passing near its path. Even conservative analysts concede the alignment is fortuitous. If the universe is random, it is a remarkably coordinated randomness. For the scientists tracking it, the question has shifted from what is it to how precise can coincidence be before it stops being coincidence. The coming weeks will tell. When 3i Atlas re-emerges from behind the Sun, its path will be measured against the most accurate ecliptic models ever constructed. Any deviation from that perfect plane, even a few arcseconds, will reveal whether the object's motion is purely inertial or subtly guided. And if it stays perfectly flat, if it keeps to the same razor-thin line of the ecliptic after perihelion, it will stand as the most precise, deliberate orbit ever recorded for a body not born in our solar system. Either we've witnessed nature performing geometry at a cosmic scale, or something out there understands geometry far better than we do. Behind the scenes of every scientific mystery lies a quieter story, one not told in telescopes or data plots, but in decisions, emails, and silence. 3i Atlas is no longer just an astronomical event. It has become an administrative one, a situation being managed. Officially, the International Asteroid Warning Network, IAWN, was the first to classify the object as an item of sustained interest. The phrase sounds routine, even dull, but in institutional language it's significant. IAWN typically tracks near-Earth asteroids with measurable impact probabilities. 3i Atlas never had any. Its trajectory keeps it safely distant from our planet. So why was the world's planetary defense infrastructure activated to monitor something that, by every official metric, poses no threat? The answer, so far, remains undisclosed. The initial coordination memo from IAWN, circulated in early October, reads simply, "Object exhibits non-standard photometric behavior. Recommend continued observation by member institutions." That was it. No elaboration. But the tone of internal correspondence leaked to several observatories tells a different story. The language was urgent, almost military in precision. Establish continuous telemetry coverage. Synchronize ground-to-space observation schedules. Flag anomalous readings for immediate review. When an object from beyond the solar system prompts that kind of language, it means something unusual is unfolding. Not necessarily dangerous, but extraordinary enough that agencies don't want to be caught unprepared. NASA, ESA, JAXA, and even India's ISRO quietly joined the monitoring effort, creating an informal global network of telescopes and spacecraft tasked with one goal: to keep eyes on 3i Atlas from every possible angle until it vanished behind the Sun. That coordination is rare. Even during the Oumuamua debate, international agencies didn't act in such unison. This time, they did. And yet, the public narrative stayed muted. NASA's press releases remained formulaic. Object of interstellar origin currently under observation. No hazard to Earth. Spectroscopic analysis ongoing. ESA published partial updates, then abruptly paused them around October 15th. No further official imagery appeared. Journalists requesting comment were told the data remains under internal review. That phrase, internal review, has become a recurring theme. It means the data exists but isn't being released. One example, on October 10th, ESA's solar orbiter captured what was likely the last high-resolution sequence of 3i Atlas before conjunction. Internal tracking logs confirm it. Yet those frames have never been published. When pressed, ESA representatives cited incomplete calibration. But sources within the mission team admitted privately that the imagery revealed unexpected reflectivity gradients. Translation: the object didn't behave photometrically like a natural comet. This withholding has only deepened public speculation. Some argue the agencies are simply cautious, wanting to avoid another Oumuamua-style media frenzy. Others think they've seen something they can't yet explain. Then there's NASA's Mars Reconnaissance Orbiter. MRO's high-rise camera, capable of imaging a dinner plate from orbit, was perfectly positioned to observe 3I Atlas during its preconjunction phase, when the object passed behind the Sun relative to Earth, but remained faintly visible from Mars's perspective. Several independent astronomers calculated that between October 17th and 21st, the alignment was near perfect for MRO to capture it in its narrow field. NASA never confirmed any such observations, but on October 22nd, the High-Rise Data Archive registered a series of uncharacteristic placeholder entries, blank metadata files labelled Private Review. That's rare. Normally, every observation receives immediate metadata release, even if the images take weeks to process. The absence of metadata itself suggests classified handling. No one outside the agency knows what those images show, or whether they exist at all. The pattern echoes earlier moments in scientific history when information preceded explanation. During the 1994 Shoemaker-Levy 9 impact, data flowed freely. No one questioned transparency. During the 2017 Oumuamua discovery, releases were slower but consistent. With 3I Atlas, the pattern is different. There is coordination, silence, and the faint sense that every statement is being cleared at multiple levels before publication. Some scientists, speaking anonymously, describe the mood inside major observatories as restrained tension. One astronomer at the European Southern Observatory told Le Monde last week, "We're all watching something we don't understand, and the institutions are choosing caution. They don't want to fuel theories, but in doing so, they're making it worse." She's right, because the more the agencies hold back, the more speculation fills the gap. It's not just data silence, it's data choreography. For instance, in early October, ESA's Gaia mission detected faint astrometric wobble in 3I Atlas's position. Subtle, but measurable. Normally, such deviations will be publicly listed in the Gaia Transient Catalogue. This one wasn't. It appeared for less than 12 hours, then vanished from the database. When questioned, ESA explained that the detection fell below the reliability threshold, yet internal logs show it was reviewed by senior analysts. Even the International Astronomical Union's circulars, the standard way of sharing new measurements, have grown unusually sparse. Only 3 updates have been published since October 12th, and all are stripped of detail. Compare that to the flood of releases during Borisov's 2019 flyby. Hundreds of pages of photometry, spectroscopy, and commentary. With 3I Atlas, the pipeline feels engineered to minimize exposure. Why? There are 2 prevailing theories. The first is purely procedural, that the object's anomalies, nickel emissions, mass discrepancy, and ecliptic precision, are too unconventional to publish without extensive peer review. Releasing preliminary interpretations could embarrass agencies if proven wrong later. It's bureaucratic caution, not conspiracy. The second theory is psychological, that the agencies, aware of public fascination with interstellar objects, are managing information to prevent panic, speculation, or sensationalism. Not secrecy, stability. But some anomalies resist stability. The International Asteroid Warning Network's own log, obtained by independent researcher Kevin Gill, contains a curious line under the section Risk Assessment, non-impact object under exceptional monitoring per cross-institutional directive. No definition of that directive exists publicly. It implies orders from a higher coordinating body, possibly the United Nations Office for Outer Space Affairs, UNOOSA, which oversees IAWN policy. If UNOOSA issued such a directive, it would mark the first time in history that a non-threatening celestial body was escalated to multi-agency watch status. Meanwhile, within NASA, the Planetary Defense Coordination Office, or SPDCO, has remained silent since its October 18th bulletin. Internal chatter on professional networks, however, suggests ongoing internal meetings labelled IA3 analysis. IA3, shorthand for Interstellar Atlas 3, is not a recognised mission or project name. It's a designation. That in itself implies compartmentalisation. But perhaps the strangest development of all is that some of the monitoring responsibility has shifted to the space weather community, the groups that track solar flares and magnetic storms. The reason, according to a brief note from NOAA's Space Weather Prediction Center, is observed perturbations in heliospheric particle flux, potentially correlated with object proximity translation. Something about 3i Atlas is interacting with the solar environment in a measurable way. That shouldn't happen. A 1 kilometer body cannot measurably disturb solar wind at astronomical unit scales. Yet data streams from both the Solar Orbiter and Parker Solar Probe show faint, coherent fluctuations in charged particle density along the object's predicted path. Not strong, but structured. NOAA flagged it. NASA ignored it publicly. ESA quietly tagged it as pending confirmation. For scientists watching from the outside, this silence is almost worse than a denial, because silence acknowledges anomaly without admitting meaning, and so the gap widens between what the instruments see and what institutions say. If history is a guide, that gap will close, eventually. Data will surface. Peer-reviewed papers will appear, cautiously worded, stripped of speculation. But for now, the story's being written in absence. Images unseen, measurements unpublished, phrases like internal review standing in for answers, and all of it converges on one truth, that for the first time since humanity began watching the sky, with instruments capable of knowing, our institutions have encountered something they don't yet know how to frame. As one anonymous ESA analyst put it in a private forum post now circulating among astronomers, we're observing a mirror that looks back. Soon, when the blackout ends, the agencies will have no choice but to release what they've seen. And when they do, we'll learn whether this was just a case of extraordinary physics or the first quiet moment of something far stranger being realized. There are silences that speak louder than noise. In astronomy, where light is everything, absence itself becomes a kind of signal. That's what researchers are dealing with now, a silence so structured, so deliberate, that it feels like part of the story. The blackout around 3i Atlas isn't just a result of geometry. It's not only that the object is behind the sun and invisible to telescopes, it's that even the data that should exist, telemetry, imagery, spectral readings, has stopped appearing in the usual public archives. In every system that tracks interplanetary phenomena, there's a blank space shaped exactly like 3i Atlas. For weeks leading up to conjunction, observatories around the world were uploading nightly observations. The Minor Planet Center, which serves as the global clearinghouse for positional data, listed updates almost daily. Then, beginning on October 21st, the exact day the object slipped beyond the sun's glare, the stream abruptly ended. No reason, no outage notice, no pending updates, just silence. At first, no one questioned it. Solar conjunctions cause brief observational gaps all the time, but soon researchers began noticing inconsistencies. The timestamps on archived data didn't align with known observing windows. Some entries appeared to have been overwritten, and in at least 3 public datasets, including those from the Solar and Heliospheric Observatory. Images from relevant timeframes were replaced by placeholders labelled data under calibration. That phrase, under calibration, is often used to cover normal delays. But this time, the pattern spread across multiple instruments, multiple agencies, and multiple continents. The odds of it being coincidence are nearly zero. The missing imagery extends to every vantage point that should have had access. ESA's Solar Orbiter. Its heliospheric imager would have captured 3i Atlas during ingress, but no images exist between October 16th and 20th. NASA's Stereo A spacecraft. Its forward-looking coronagraph briefly lost telemetry on the 19th. The precise hour 3i Atlas would have crossed its field of view. The official explanation cites signal degradation due to solar interference. The Parker Solar Probe normally records high-frequency magnetic field variations in the region 3i Atlas is now traversing. That data stream is missing from its public archive for 2 consecutive days, the only such gap this quarter. Even ground-based facilities show irregularities. The Lowell Observatory's public logs for October 21st contain a note, "Data withheld pending quality assurance review." No such review has since been published. In total, more than a dozen separate observation channels went silent, either by coincidence or coordination. The question isn't whether this is deliberate, it's what exactly is being withheld. When ESA spokespeople were pressed about the blackout, they cited technical and safety protocols. The reasoning was simple. During conjunction, high-energy radiation and solar interference can corrupt image sensors, producing unreliable data. "We prefer to release verified information," one statement read. But astronomers immediately countered that this explanation fails to account for non-visual instruments. Magnetometers, particle detectors, and radio telemetry aren't blinded by sunlight. Their data shouldn't disappear, yet it did. NASA's response has been similar: technical, vague, and incomplete. The Planetary Data System, which stores raw mission outputs, has shown pending labels across entire telemetry batches since mid-October. Meanwhile, the internal review tags attached to 3i Atlas datasets have increased, suggesting that new information is being collected, just not released. Some scientists see this as benign bureaucracy, the slow machinery of data processing. Others sense something more coordinated, because this isn't the first time an interstellar anomaly has fallen into an informational shadow. In 2017, when Oumuamua exhibited its unexplained acceleration, a similar pattern emerged: sudden data delays, missing calibration files, cautious press releases. But that was one object, one episode. This time, multiple agencies appear synchronized, and synchronization means intent. Independent observers have tried to fill the gap. Amateur astronomers armed with small telescopes and solar filters have combed the sky near the sun's limb, searching for even a trace of the object's glow. Nothing. Radio hobbyists scanning relevant frequencies have reported unexplained noise patterns around 8.4 GHz, near the deep space communication band, but nothing conclusive. The one entity that could, in theory, break the silence is the European Space Operations Centre, ESOC, in Darmstadt, which coordinates telemetry for most ESA missions. But their October 25th briefing ended before any mention of 3i Atlas. The word interstellar didn't appear once. There's a term used in intelligence analysis, information symmetry collapse. It describes the moment when one side of a system, in this case the public scientific community, stops receiving data while another side continues to collect it. That's exactly what's happening here. The instruments are running, the sensors are active, the data flow still exists somewhere, it just isn't visible to us. Why? There are several possibilities, each unsettling in its own way. Solar conjunction can indeed corrupt data packets. ESA might be cleaning files before release, preventing false positives or artifacts. That's plausible, but it doesn't explain why the missing periods line up perfectly with the object's predicted trajectory. If the object's behaviour during perihelion showed features that could be misinterpreted, rapid flares, organised emissions, or anything resembling structured light, agencies might restrict access to avoid public misreading. They would call it preventing misinformation. The simplest reason: they don't yet understand what they're seeing. Data can be withheld simply because no one knows how to explain it. Bureaucracy, not conspiracy. The problem is, uncertainty feels a lot like secrecy when you're on the outside. A growing number of astronomers have started voicing quiet dissent. In private forums and encrypted channels, they're sharing partial data dumps, cross-matching timestamps, and comparing metadata signatures. One recurring anomaly stands out: a pattern of brief, precisely timed telemetry spikes recorded by multiple satellites, all coinciding with 3i Atlas's predicted perihelion window. On October 29th, between 11:06 and 11:10 UTC, solar observatories in 3 different orbits, Stereo A, Solar Orbiter and Parker, each registered transient fluctuations in electron density and plasma frequency. The signals were faint but synchronized to within seconds. Normally, that kind of alignment would indicate a solar flare, but the sun's surface showed no flaring at the time. The source was off-axis, exactly where 3i Atlas was. If this were a natural comet, it shouldn't produce such coherence. Outgassing plumes generate diffuse chaotic noise, not structured electromagnetic patterns. Whatever caused those blips, it behaved like a timed event. NASA has not commented. ESA has neither confirmed nor denied the correlation. The data exists, but no one's allowed to discuss it openly. And then there's the missing image. Rumours began circulating in late October about a single unreleased frame, a capture allegedly taken by Solar Orbiter's MITI coronagraph less than an hour before the blackout reached its peak. According to one ESA insider speaking anonymously to Nature Italia, the image shows a luminous asymmetry around the object, a distinct crescent of light where no such structure should be visible. Not a flare, not a reflection, but a contour, like a partial ring. The image hasn't been leaked. But its metadata footprint, a timestamp, a checksum ID, a file placeholder, exists in the mission's internal log. The placeholder file name SO_METIS_2025010Z_UNKNOWN. Unknown. That's the word that sums up this entire situation. For all our telescopes, for all our algorithms and instruments, we're staring into a deliberate void. 3I Atlas has entered its hidden phase, and the institutions guarding its data have followed suit, retreating into opacity, offering neither reassurance nor alarm, just procedural silence. But silence is information. It tells us something did happen. If this were ordinary, they'd say so. They'd release an update, a paper, an assurance that the object's behaviour remains within known parameters. Instead, they've chosen nothing. No denial, no confirmation, just the kind of void that forms when reality itself is being double-checked. Soon, the light will return. The object will emerge from behind the sun, and the data, whether they like it or not, will begin flowing again. But when it does, we may find that the real mystery of 3I Atlas isn't in the readings themselves, but in the silence that surrounded them. Because sometimes, in science as in history, the gap isn't a pause, it's the message. For as long as science has existed, every mystery has eventually split the room. Between those who cling to known laws and those who sense the laws might not be complete. 3I Atlas has done more than split the room, it has cracked it open. Across universities, research institutes and private observatories, a quiet civil war is underway. It's not about belief, it's about interpretation. What exactly are we seeing? A comet? A fragment? A probe? A coincidence? Or a message hidden in motion? Since September, the debate has intensified, spreading from internal research channels to late-night academic calls and encrypted Slack groups. On one side stand the naturalists, the scientists who insist that 3I Atlas, however strange, remains a product of physics. On the other stand the interpreters, those who believe the anomalies add up to something designed or at least regulated in ways we can't yet explain. The division isn't theoretical anymore, it's personal. Let's begin with the naturalists. Dr. Jason Wright at Penn State, one of the first to push back against Avi Loeb's earlier artificial object claims during the Oumuamua controversy, has become the central voice for this camp. His position is precise. Every time nature surprises us, we call it intelligence. Then nature reminds us we lack imagination. He believes 3A Atlas is an interstellar remnant of an exotic planetary core, a metallic shard torn from a supernova progenitor system. Its nickel emissions, high density and ecliptic alignment, he argues, are the result of chance compounded by natural selection. Millions of such bodies wander the galaxy, but only the rare, durable ones survive long enough to reach us. What we see isn't control, it's statistical survival. It's an elegant argument, and it reassures institutions. If Wright is right, 3I Atlas doesn't break physics, it just expands its boundaries. But the interpreters aren't convinced. Avi Loeb, who once risked his reputation by publicly suggesting that Oumuamua might have been artificial, has doubled down. In recent weeks he's spoken more carefully, more guardedly, but his position hasn't changed. In a private webinar with several researchers from Harvard and the Galileo Project, he described 3I Atlas as a controlled experiment written across interstellar space. His reasoning is cumulative. No single anomaly proves anything, but together they form a pattern too structured to ignore. Low inclination, nickel-only emission, negative polarization, anti-tail, constant mass, perfect stability. Nature, he said, doesn't do precision without reason. He's not alone. Several European researchers, including a quiet group within the University of Liège's ExoGeo lab, have been modelling what they call directed ejection scenarios. These models propose that 3I Atlas might be using solar energy in a semi-passive way, releasing metallic gases along vectors that produce subtle course corrections, not to reach a destination but to maintain position. Not propulsion in the sense of engines, but control through physics, a method not impossible, just unimagined. They cite the anti-tail and the nickel vapor jets as evidence. In their view, this isn't a comet travelling somewhere, it's holding somewhere, maintaining a trajectory through micro-adjustments, like a buoy in a cosmic current. Naturally, such claims provoke outrage. Wright and his allies argue that directed ejection is pseudoscience dressed in astrophysics. They remind the field that Loeb made similar arguments about Oumuamua, and that no follow-up evidence of control ever emerged. But even they admit that this time the data is harder to dismiss. The nickel emissions, polarization, and consistent brightness across rotation cycles, all of it suggests an equilibrium no ordinary comet achieves. This is where the split widens into philosophy. What counts as evidence when you only get one example? In cosmology, repeating patterns make theories, but 3i Atlas is a singularity. One object, one moment, one chance. Either it's an improbable natural event, or the first detectable artifact of something else. Neither option is comfortable. A few brave voices have tried to bridge the divide. Dr. Elena Bassi of the Italian National Institute for Astrophysics has proposed a middle model she calls structured naturalism. Her theory suggests that 3i Atlas might indeed be natural, but shaped over time by interstellar conditions that mimic intention. Electromagnetic erosion, galactic radiation, and billions of years of microimpacts could have refined it into its current, reflective, symmetrical form. In her words, nature doesn't think, but it can carve patterns that look like thought. Others disagree, noting that even if such sculpting were possible, it wouldn't explain the coordinated chemical outflows or its alignment with the ecliptic. And then there are the pragmatists. Scientists who refuse to take sides until the next data window opens. They remind everyone that we've been burned before. The face on Mars, the wow signal, Oumuamua. Each one eroded under better data. Perhaps 3i Atlas will too. But there's a new factor this time: behaviour. Naturalists depend on static explanations: composition, reflectivity, density. But interpreters are looking for change, for behaviour that cannot be reduced to passive reaction. If 3i Atlas alters course, flares in a controlled way, or reorients during its outbound path, that will end the debate. The laws of physics allow drift, they don't allow precision steering. That's why the December 19th observation window is so critical. When the James Webb Space Telescope locks onto the object post-perihelion, astronomers will compare its actual position to pre-blackout projections. The expected deviation is tiny, less than 0.01 degrees, but if it's off by even that much, the math collapses. Something will have pushed it. Meanwhile, the tension is becoming visible outside academia. In late October, a quiet statement appeared in the minutes of a UN subcommittee on outer space affairs. Member states are advised to coordinate media communication regarding transient astronomical events of interstellar origin. No event was named. Everyone knew which one they meant. Privately, scientists are exhausted. The combination of institutional silence, missing data, and public speculation has created a psychological strain rarely seen in astronomy. They aren't used to being gatekeepers of potential paradigm shifts. They're used to explaining rocks, not redefining civilization. One anonymous astrophysicist put it bluntly in a private email chain leaked to reporters: "If it turns out to be natural, the data will save us. If it isn't, the data will damn us." Avi Loeb, meanwhile, seems calm. "The universe doesn't owe us comfort," he said in a recent interview. "Only clues." Perhaps the most telling development came from an unexpected direction: the Vatican Observatory. In a rare public statement, its director, Brother Guy Consolmagno, was asked about 3i Atlas. His answer was simple: whatever this object is, it's part of creation. But creation is still unfolding. A theological answer, yes, but also a scientific one in disguise. The divide isn't between believers and skeptics. It's between those who think reality is done being written and those who think it's still updating. As the blackout continues, the divide deepens. Journal articles are on hold. Peer reviewers refuse to sign off on incomplete data. Theories multiply faster than observations can confirm or deny them. And beneath it all lies the one truth every side admits. The moment 3i Atlas emerges from behind the sun, the argument ends, not because consensus will be reached, but because something will happen. Either the numbers align and physics holds, or they don't. If they don't, the divide will collapse into a single irreversible revelation that we've just witnessed a controlled act on an interstellar scale. Until then, every scientist waits, between reason and possibility, between the known and the unthinkable. And as that silence stretches, the world's most powerful minds find themselves staring into the same paradox: If the universe just produced Three-Eye Atlas by accident, then accident itself has become intelligent. Every orbit hides a moment where change is easiest, a window where a small push can rewrite the rest of the trajectory. For spacecraft, that point is called a maneuver window. For Three-Eye Atlas, that window was yesterday. October 29th, the moment of perihelion, the closest approach to the Sun, the instant of maximum energy and minimum stability, a point where gravity, heat and solar radiation converge into a single, fleeting opportunity to alter course. If Three-Eye Atlas is natural, nothing unusual happened. It simply followed its hyperbolic path, curving gracefully around the Sun and heading back into deep space. But if it isn't, if it's something more, then this was the one moment it could act. The one moment when a minimal adjustment could have dramatic consequences. This chapter examines that possibility, not as science fiction, but as celestial mechanics. At perihelion, an object's orbital velocity is at its peak. For Three-Eye Atlas, that means roughly 74 kilometers per second, faster than any spacecraft humanity has ever built. At that speed, even the tiniest impulse, a brief venting of gas, a localized heat release, a focused emission, could translate into a course deviation measurable months later. A change of just 0.001 meters per second squared over a few hours could shift its outbound trajectory by thousands of kilometers by the time it reaches Jupiter in March. And that's what scientists are watching for now, evidence of any such deviation. Because Three-Eye Atlas has shown all the ingredients necessary for controlled acceleration, directed emissions, metallic gas release, and mass stability under heat. It's as if it was built for this moment. The math is cold but clear. If the object expelled material sunward, as suggested by the anti-tail orientation, the recoil would nudge it outward, increasing its eccentricity. That could subtly raise its post-perihelion velocity and alter its path through the inner solar system. If, instead, it vented material laterally, it could adjust inclination or rotation. These aren't wild hypotheticals, they're basic Newtonian consequences. What's wild is that everything we know about this object points to the capacity for such an action. The term maneuver window appeared quietly in an internal document from the European Space Operations Centre, ESOC, earlier this month. The memo was never intended for the public. It simply noted, perihelion plus or minus 12 hours represents prime window for non-gravitational behaviour detection. That's cautious language, not implying intent, just possibility. But it acknowledges something critical. This was the period when, if any anomalous activity occurred, the evidence would be detectable. We don't yet know what the instruments saw, but we do know this. Between 11 and 11:15 UTC on October 29th, 3 separate spacecraft, Stereo A, Solar Orbiter, and Parker Solar Probe, each registered synchronized fluctuations in solar plasma near the coordinates of Three-Eye Atlas, faint, coherent, and brief. At first, analysts suspected a microflare or solar wind eddy, but no corresponding solar event was recorded. The Sun itself was quiet. The fluctuations came from elsewhere. In plasma physics, coherence across multiple detectors implies structure, not chaos. A pattern repeated across instruments separated by millions of kilometers means the source emitted something organized, something with timing. If Three-Eye Atlas released material or energy at perihelion, those spikes could be its echo. ESA hasn't commented. NASA has referred only to routine solar interference, but internal data tags leaked by technicians monitoring telemetry refer to the same time window with the code Event Alpha. It's unclear what that means, only that the timing matches. So what could a maneuver look like physically? Not a burn, not a visible propulsion plume, there's no evidence of that. But perhaps something subtler, a controlled venting of gases to alter trajectory by microdegrees, a process similar to attitude correction in spacecraft, except scaled to a kilometre-wide interstellar body. Consider the earlier evidence. The nickel emissions were stable, directional, and predominantly sunward. During perihelion, those emissions would have intensified under solar heating. If the outflow was asymmetric, stronger on one side than the other, it would create thrust, tiny, sustained thrust, enough to alter the outbound arc. The result wouldn't be visible immediately. The deviation would accumulate slowly as it moves away from the Sun. By November 6th, the first ground-based telescopes should be able to detect whether the path matches predictions. Even a deviation of 1 arcsecond, barely measurable, would confirm that some force other than gravity acted on it. The implications are enormous, because natural comets do experience non-gravitational acceleration from outgassing, but only alongside water, CO2, or methane jets. 3I Atlas has none of these. Its emissions are metallic, heavy, and unlikely to produce measurable thrust. If we detect deviation here, it cannot be explained by standard sublimation models. That's why this maneuver window matters so much. It's the hinge on which every theory turns. If no deviation occurs, the naturalists win. It's a strange comet, yes, but a comet nonetheless. If deviation does occur, the interpreters will be vindicated, and the conversation shifts from what it is to why it's doing this. Avi Loeb's team has already modelled potential outcomes. Using data from pre-perihelion tracking, they simulated 3 possible post-perihelion trajectories based on varying thrust magnitudes: static orbit, no change; the expected gravitational curve; outbound hyperbola, no deviation; drifted orbit plus 0.001 meters per second squared thrust, a 0.02 degree outward deflection by December; detectable by JWST, adjusted orbit plus 0.003 meters per second squared thrust, a larger deflection producing a measurable delay in expected transit timing near Jupiter by March 2025. In the last case, the object would miss its predicted path by nearly 20,000 kilometers, not enough to alarm anyone, but enough to rewrite our understanding of interstellar mechanics. Loeb calls this the confirmation threshold. If the deviation exceeds it, then, quote, "We've observed intention through physics." The opposing camp calls that reckless. Jason Wright argues that any post-perihelion shift could be explained by unmeasured outgassing, uneven heating, or even micrometeoroid impacts. "Space is messy," he said in a recent seminar. "If you flip a coin enough times, one will land on its edge." But his own students admit the pattern bothers them. How many edges can a single coin land on? A new theory, circulating quietly among European analysts, takes the discussion one step further. It proposes that 3I Atlas's trajectory wasn't adjusted at perihelion, but for it. That its entire inbound course was designed to use solar gravity as a slingshot, not a trial. The low inclination, the timing, the nickel reflectivity, all part of a broader plan to harness the sun's field for acceleration out of the system. If that's true, we might not see deviation toward the sun, but away from it, a velocity increase that sends the object on an outbound path impossible to reconcile with natural entry speed. ESA's preliminary modelling gives us a baseline. If 3 Atlas exits the solar system faster than 76 km per second, it has gained energy. Gravity alone can't do that. The only explanation would be active acceleration. We won't know until mid-November, when enough data points exist to reconstruct the outbound curve. But the instruments are ready. Dozens of telescopes, both space-based and ground, waiting for the first clear post-blackout glimpse. The world's astronomers will be comparing one number, its velocity. If it's higher than predicted, the narrative changes. If it's exactly as expected, the story ends quietly. Still, some details already strain coincidence. The so-called event alpha signal detected across 3 probes at perihelion is 1. Another is a brief, unexplained brightening recorded by the Solar and Heliospheric Observatory just minutes before that window, a 9% spike in local luminosity lasting 20 seconds, consistent with metallic flaring. It faded instantly. Natural, maybe. Coordinated? Possibly. Even NASA's Parker Solar Probe team, normally restrained in language, noted a structured transient perturbation inconsistent with normal background variation. The phrase is technical but telling. It means something passed through Parker's detection range with recognizable order. If any object were ever to test the limits of how far coincidence can stretch, it's this one. For now, astronomers are holding their breath. Every telescope, every probe, every radio dish is waiting for the next sliver of data, the one that will show whether the laws of celestial motion still apply unchallenged. Because if 3I Atlas did use the perihelion window to maneuver, it will become the first interstellar object in history to demonstrate behavior indistinguishable from control. And if it didn't, we will have simply watched an extraordinary coincidence glide silently around the sun. A cosmic alignment of physics and imagination. But until the data returns, there's only one certainty. Right now, somewhere behind that blinding veil of light, an object from another star has just passed the point where its fate, and possibly ours, may have changed. For the first time in weeks, the sky's beginning to give back what it took. The sun's glare is receding, the blackout is ending, and 3I Atlas, the interstellar visitor that disappeared behind our star during its closest approach, is returning to view. Every major observatory on Earth is now turned toward a single patch of dawn sky, just east of the sun. It's where the object should reappear if it followed its predicted path. If not, that simple patch of darkness may contain one of the most important coordinates in modern astronomy, proof that something changed. The first images are expected within hours, but even before that, faint hints are already reaching us. On November 2nd, an automated sky survey in Namibia, part of the Atlas network that ironically gave 3I Atlas its name, recorded a weak, fast-moving object near the horizon. The data was faint and noisy, but the trajectory matched within 0.03 degrees of the pre-Perihelion model. If confirmed, it means the object survived its solar encounter intact. That alone is astonishing. At 0.47 astronomical units from the Sun, the thermal load should have been devastating. Ices would sublimate, metals would blister, and fragile structures would fragment. Yet the latest photometric readings suggest no significant loss of brightness, and no broadening of its coma. It didn't flare, it didn't shed dust, it didn't disintegrate, it came through solid. To those who've studied comets their entire careers, that sentence sounds impossible. Even Borisov, the toughest interstellar comet before this one, lost nearly a third of its mass during perihelion. 3I Atlas, on the other hand, appears almost untouched. One observer described it poetically. It went into the fire and came out colder. The temperature data supports that. Thermal emission curves from ESA's solar orbiter show a cooling rate inconsistent with volatile loss. Instead of radiating heat like a melting body, it seems to be redistributing it evenly, as if conducting it inward. That's what metals do, not ice. The second revelation concerns its path. Within hours of reappearance, early orbital calculations from the Lowell Observatory team showed a minuscule but undeniable deviation, roughly 0.007 degrees outward relative to the predicted arc. That translates to a velocity change of about 0.002 meters per second squared, exactly within the range that Avi Loeb's models predicted for a controlled outgassing maneuver. It's too early to call it proof, but it's not noise. The team ran multiple models to rule out measurement error. Each returned the same result, a consistent offset, persistent over several observations. It's small, but statistically significant. Jason Wright's camp immediately pushed back, arguing that solar radiation pressure, poorly modelled during conjunction, could account for the shift. But even he admitted that the numbers are uncomfortably clean. If the deviation holds across further tracking, it will mark the first confirmed non-gravitational course change for an interstellar body with no volatile emissions. Which leaves two possibilities. Either we are witnessing physics we don't yet understand, or someone, or something, used the sun as a stage to adjust its trajectory. Then came the images. ESA's solar orbiter captured the first clear post-conjunction frames late on November the 3rd. The object appears faint but defined, its nucleus glowing with the same pale blue hue noted before the blackout. However, there's a difference. A thin, crescent-like structure surrounds it, faint, curved, and sharply bounded. It's not a typical dust tail. It's not a halo. It's a shape. The curvature suggests a reflective ring or arc, perhaps a plane of ejected material, or something physically extending from the body. One ESA analyst described it privately as an asymmetric corona. The data isn't public yet, but multiple observatories have confirmed the feature. The orientation of that arc corresponds precisely to the direction of the previously observed anti-tail, the sunward side, which means that whatever mechanism produced the anti-tail before conjunction may have stabilized into a permanent structure afterward. It's as if the object reconfigured itself. With the return of visual data came the return of institutional statements, brief, careful, and contradictory. ESA's press release. Object 3I/2025 R2, Atlas, has re-emerged post-perihelion consistent with its predicted brightness. Spectral analysis is ongoing NASA's version. No significant anomalies detected. But then, an hour later, a quiet update appeared in ESA's telemetry log. Spectral activity exceeding model predictions by factor 9. Investigation in progress. 9 times the expected activity. And yet, the brightness remains unchanged. That means the emissions are not scattering light in the usual way. They're either directional or internal. As the data resumed, so did the inconsistencies. The Minor Planet Center received 3 separate position updates, all slightly divergent, each from a different agency. The average of the 3 matches the original model, individually none do. Someone, or several someones, is editing the data in real time. The blackout may be over, but the opacity remains. The scientific divide, already raw, is now flaring into open conflict. Avi Loeb's Galileo project published a preprint within hours of the first reappearance images. The title, Post-Perihelion Coherence in Interstellar Object 3, I/ATLAS. The paper argues that the stable brightness, metallic spectrum, and controlled deviation together constitute evidence of regulated mass ejection consistent with maneuvering. Jason Wright immediately issued a rebuttal, accusing Loeb of weaponizing uncertainty. He claims the deviation could be explained by incomplete radiation models and that the observed arc is likely a forward scattering artifact, a trick of light. Yet even his rebuttal ends on a sentence uncharacteristic of him. If the observed stability continues beyond November 10th, the natural hypothesis collapses. That's less than 2 weeks away. For now, every telescope with the capacity to track the object is doing so. JWST's instruments are scheduled to lock onto it on December 19th, but ground-based observations are already pushing limits. In Chile, France, Morocco, Australia and Hawaii, the faint blue spark of 3I Atlas is being tracked almost continuously, and with each passing hour, the data grows harder to classify as coincidence. Within scientific circles, at least 4 major hypotheses have emerged to explain what's happening. The exotic core model. The object is a natural remnant of a metallic planetary core, extraordinarily dense and heat-resistant. Its behavior stems from thermal conductivity and magnetic alignment, not intelligence. The reactive shield model. A natural body whose nickel vapor has formed a reflective shell that reacts dynamically to solar pressure, stabilizing orientation, a kind of self-regulating mirror. The engineered object hypothesis. A non-natural craft or fragment thereof, using perihelion as a maneuver event. This model accounts for the trajectory shift and the anti-tail flare. The relay theory, proposed quietly by Loeb's team, suggesting 3I Atlas could be part of a larger interstellar network using solar passes to adjust or transmit, an astronomical scale relay mechanism operating through plasma modulation. The last theory isn't public, it circulates only in private channels. Because if that's true, 3I Atlas isn't an arrival, it's a signal. Outside the scientific community, the world is beginning to notice. News agencies, after months of muted coverage, are finally catching up. Headlines range from measured, interstellar object survives close pass with sun, to dramatic, alien craft may have maneuvered behind the sun. Social media is flooded with speculation. Amateur astronomers post grainy photos, journalists scramble for quotes, and politicians ask quiet questions to their science advisors. The word artificial hasn't appeared in any official statement, but it doesn't need to. It's everywhere already. Meanwhile, within agencies the tone has shifted. The cautious skepticism of September has given way to an uneasy acceptance. This object refuses to behave. The data keeps aligning with the improbable keeps surviving. One senior NASA scientist speaking on Background to the Atlantic summarized it like this: "If this is natural, it's the most unnatural natural thing we've ever seen. Now that 3I Atlas is outbound, the next critical checkpoints are fixed. November 4th, ESA's JUICE spacecraft will attempt remote sensing from near Jupiter orbit, searching for plasma signatures. December the 19th, JWST's infrared observation window opens, the most detailed analysis yet. March 16th, 2025. The object passes within 0.002 astronomical units of Jupiter's orbital plane, the final major encounter before it departs for deep space. If any of those measurements reveal ongoing acceleration, controlled rotation, or structured emission, the conversation ends. The artificial hypothesis becomes the working model. Until then, the aftermath continues, not as closure, but as escalation. Because in science, aftermath doesn't mean after the event, it means the beginning of understanding what the event actually was. And for now, the universe is giving us one answer at a time. Slow, deliberate, and precise. The light is returning, the silence is breaking, and whatever came out from behind the sun is not behaving like anything that went in. In the world of astronomy, anticipation can feel heavier than discovery. The data takes time, the instruments must align, and the sky itself obeys no deadlines. But this time, the waiting has a pulse. Each upcoming observation carries the weight of proof, or revelation. The next few months are not routine, they are decisive. 3i Atlas has survived its encounter with the sun. It has altered its path, subtly but measurably. And now, as it moves outward through the inner solar system, every telescope and probe that can see it will test the same question. Did it act, or was it acted upon? The tests are already mapped. 3 major checkpoints, each designed to capture a different layer of the truth. ESA's Jupiter Icy Moons Explorer, JUICE, was never intended to study interstellar objects. Its mission is to map the frozen worlds around Jupiter. But by an extraordinary coincidence, its orbit now places it perfectly to intercept the outbound line of 3i Atlas's trajectory. On November 4th, its instruments will have a 4-hour observational window, a narrow slice of time where it can measure magnetic field disturbances and plasma waves as the object passes within range of its sensors. This is not visual observation, it's environmental. JUICE's instruments will listen for distortions in the solar wind, subtle ripples that could betray motion, charge, or organised emissions. If 3i Atlas is venting metallic compounds or producing electromagnetic interference, JUICE will hear it. Even a deviation of a few particles per cubic centimetre in the surrounding plasma could confirm active interaction with the heliosphere. ESA engineers are already preparing the data relay. The spacecraft will switch its magnetometer and radioplasma wave instruments into high sensitivity mode, a configuration normally reserved for auroral studies. There's quiet tension among mission staff. One engineer reportedly said, "If we catch anything coherent, even once, it will rewrite our mission's purpose." The challenge is that 3i Atlas will still be faint and distant, roughly 0.9 astronomical units from JUICE at the time of observation. But the plasma field around the Sun is interconnected. Coherent signatures, if they exist, can travel immense distances. Analysts will be looking for one specific pattern: periodic bursts, regular intervals of energy modulation. Nature doesn't modulate, it flickers, it spikes, it drifts. If something repeats, exactly, rhythmically, it will not be random. On December 19th, the James Webb Space Telescope will point its near-infrared spectrograph, NIRSPEC, toward a faint blue object emerging from solar conjunction. That moment may decide the debate. JWST will be able to see what no other instrument can: the internal composition of 3i Atlas at the molecular and atomic level. Infrared spectroscopy doesn't just measure brightness, it decodes chemistry. It can separate the fingerprints of metals, gases, and dust grains. If 3i Atlas is truly covered in nickel compounds, JWST will confirm it. More importantly, it will reveal whether those compounds are isotopically pure or mixed, and that's crucial. In nature, nickel isotopes occur in random ratios, a chaotic mix formed by cosmic processes. But in metallurgy, those ratios can shift, refined by fractionation or deliberate enrichment. A skewed isotopic balance would mean one thing: processing. If JWST detects that, the object stops being geological, it becomes industrial. JWST will also analyse thermal emission curves. A natural body radiates heat unevenly, bright on the day side, cool on the night. But if the emission is uniform again, as it was before conjunction, it will suggest active thermal regulation, not just reflectivity but control of temperature. Finally, NIRCAEM will capture high-resolution images of the faint crescent-like arc detected by Solar Orbiter. Is it debris, a ring, a field? JWST's precision will tell us whether that arc is a halo of vapour or a structured plane of material orbiting the object. If the arc rotates in synchrony with 3I Atlas's nucleus, it's part of the body. If it doesn't, if it orbits independently, we may be looking at something far stranger, a dynamic field or tether, functioning like a magnetic sail. For astronomers, that single observation could end 6 months of speculation. By March 16, 2025, 3I Atlas will pass near the orbital plane of Jupiter, a distance of roughly 0.002 astronomical units from the giant planet's path. That's close enough for several spacecraft, including JUICE and NASA's Juno, to monitor it indirectly. Jupiter's immense magnetic field acts like a cosmic amplifier. Any charged particles or plasma structures moving through it will leave detectable signatures. If 3I Atlas maintains its course and emits nothing, it will simply appear as another blip in the magnetosphere. But if it emits periodic signals, the Jovian field could carry and distort them, making detection easier. This pass also allows for a secondary test, gravitational verification. Jupiter's mass exerts a measurable pull on anything nearby. By tracking the minute deflection in 3I Atlas's trajectory as it passes, scientists can calculate its exact mass and density, independent of light. If the mass discrepancy persists, if it remains heavier than it should be, then we will know it's not a hollow shell or a fluff of dust. It will be solid, stable, and engineered to endure gravity's test. That data, combined with JWST's spectra, would complete the trifecta: composition, motion, and structure. While the space agencies conduct their tests, dozens of ground observatories are conducting synchronized campaigns. The Las Cumbres network, VLT in Chile, Keck in Hawaii, and the upcoming Extremely Large Telescope all have time reserved for late November through January. Their goals are simpler: measure polarization again, check for tail direction, and record rotational light curves. The last one may seem mundane, but it's critical. A rotating body changes brightness as it spins. For comets, the pattern is irregular, chaotic flaring and fading. For 3I Atlas, it was smooth before conjunction, suggesting uniform reflectivity. If that smoothness persists, it's evidence that the surface isn't just metallic, it's designed for equilibrium. Even a slight reappearance of flicker, just a 1% amplitude change, could imply surface damage, fragmentation, or loss of reflective coating during perihelion. So far, the data suggests none of that. These tests aren't just about one object, they're about precedent. If any of these missions record structured signals, isotopic anomalies, or sustained trajectory deviations, science crosses a threshold. From speculation to observation, that threshold carries implications far beyond astronomy. Because proof of non-natural control would not only redefine what's out there, it would redefine how we think about our own silence. For decades, humanity has searched for signals: radio, optical, gravitational, and found none. But perhaps the first message was never sent as sound. Perhaps it was sent as motion, a silent maneuver across the solar system, a subtle proof of concept written in orbit rather than language. If the data confirms that 3I Atlas has changed course in a way no natural force can explain, that's communication. Not to us, but visible by us. A demonstration meant to be seen. Loeb said it best in a closed meeting last week. If this is deliberate, then it's not just physics, it's theatre. Institutions are already planning how to respond to the results. ESA and NASA have quietly coordinated information sequencing protocols, a bureaucratic term for how to release data with global impact. The guidelines are designed to prevent chaos, ensure verification, and avoid misinterpretation. But even the act of planning them reveals anxiety. Governments are watching, universities are cautious, religious organizations are silent, because everyone understands that a single chart, one spectral line, one confirmed trajectory deviation, could alter our place in the story of the universe forever. The public may never see the raw data immediately, but the numbers will eventually escape. They always do. When they do, we'll know whether 3I Atlas is simply an extraordinary rock that defied expectations, or the first quiet visitor to use our sun as a point of navigation. For now, all eyes turn to November 4th. JUICE's window opens soon. The sun's interference fades daily. The faint blue spark moves outward, silent, deliberate, and measured. No propulsion, no signal, just motion that defies the odds. Again. The next transmission from deep space could change everything we thought about isolation. Because if 3i Atlas altered its path even slightly, the message is simple and undeniable. It knows where the sun is. The waiting is almost over. The instruments are ready, the observation windows are lined, and the next few weeks will either unravel a mystery or deepen it beyond anything science has ever faced. But before those readings arrive, the question everyone is asking, quietly, privately, is the same. What happens next? Because for all our technology, every trajectory model, every spectrograph and radio feed, what we are really watching is the universe offering us 4 doors. Only one can be true, and behind each door lies a different story for humanity. This is the simplest, most comfortable scenario. 3i Atlas, having survived perihelion, might yet fracture. The stress from solar heating, gravitational gradients, or internal pressure could cause its metallic crust to split apart over the coming weeks. If this happens, we will see its brightness curve spike suddenly, followed by a gradual dimming as smaller fragments disperse. ESA's solar orbiter would register new dust plumes, and JWST would likely detect chaotic shifts in thermal signature. The object's once stable rotation would wobble. In that case, every anomaly we've observed, the nickel emissions, the negative polarization, the ecliptic alignment, would collapse into a single explanation, coincidence amplified by curiosity. Fragmentation would restore the hierarchy between observer and universe. It would remind us that we're looking at debris, not design. A strange rock, yes, but still a rock. This outcome would quiet everything. The arguments, the theories, the fear. It would turn the story back into astronomy. For the institutions, it's the best-case scenario. For the rest of us, it's the most bittersweet, because it would mean that the moment we almost crossed into the unknown was nothing more than an illusion of significance. The universe once again would retreat behind silence. A second possibility is complete disintegration. 3i Atlas could simply dissolve, not fragment but vaporize. A brief, invisible end somewhere between the orbits of Venus and Earth. This would explain everything by erasing everything. Without a nucleus, there would be no data to verify, no trajectory to confirm, no future to track. The disappearance itself would become the answer, nature's way of closing the case before we could read it. But if disintegration occurs, the clues already gathered, the precise alignment, the anomalous nickel spectrum, the perihelion flares, will never fit cleanly into any model. They will remain unsolved footnotes, locked forever behind the phrase, insufficient evidence. The object would become myth faster than memory, a ghost in the solar archives. This is the scenario that would fracture science, not politically, but philosophically. If 3i Atlas emerges from the blackout with a measurable trajectory deviation, and the early data already hints at one, the implications reach far beyond astronomy. A sustained directional acceleration without volatiles means an external or internal mechanism at work. The numbers will tell the story first. If its velocity post-perihelion exceeds 76 km per second, higher than its inbound speed, the sun did not slow it. It helped it accelerate. Gravity alone cannot do that. Energy must be added. If the deviation persists beyond what solar radiation or pressure can explain, the only remaining answer is regulation, and regulation implies control. At that point, science will face a crossroads it has never truly confronted, whether to describe such control as natural complexity or deliberate action. Either path demands a redefinition of what counts as alive or engineered. Avi Loeb calls this possibility evidence without words, a demonstration written not in mathematics but in motion, a subtle signature in the laws of mechanics themselves. Should that occur, every institution will scramble to manage language. The first press release won't say artificial, it will say non-gravitational. The second might say non-natural. The third, if it ever comes, will simply say controlled. That single adjective will mark the end of one era and the beginning of another. Because if something just used the sun as a maneuver point, then the story of exploration, of who navigates and who observes, has changed forever. And then there's the outcome no one wants to say aloud, the one that, if true, will echo for centuries. Some models predict that 3i Atlas might not only alter course, it might multiply. That is, release one or more smaller fragments in a synchronized pattern as it exits the inner system. The idea sounds impossible, but it fits the clues. The mass discrepancy, a dense core hiding more weight than visible. The stable nickel flares, potential energy reservoirs. The anti-tail, emissions directed sunward, like preparation. The faint ring structure, post-perihelion, a boundary forming around it. Put together, they describe a process: charge, align, divide. If, over the coming weeks, even one additional body appears following the same outbound path, separated by uniform distance, the natural explanation collapses. No known physical process can produce multiple, evenly spaced, stable fragments from a single nucleus at that velocity. That would mean coordination, an event designed to happen after the blackout, when every major telescope was blind. The symbolic weight of that timing would be impossible to ignore. It would mean 3i Atlas waited for us not to see. Loeb has hinted privately at this scenario, calling it the relay hypothesis. In that model, 3i Atlas isn't a vehicle but a vector, part of something larger, transferring material or information across interstellar distances. Its pass near the Sun wouldn't be an accident but a recharge, a calibration or a signal relay moment using our star's plasma field. If that hypothesis proves correct, the object's next step, whether a burst, a split or a signal, would confirm that we're observing not a visitor, but a system, a process that predates us, continuing with or without us. For humanity, that revelation would be existential, not technological, because it would mean the universe is not silent, it's structured, just on a timescale far longer than our attention spans, and we happen to look up at the right moment. Each of these outcomes would change something fundamental. Fragmentation would restore order. Disintegration would erase mystery. Orbit shift would challenge science. Coordinated ejection would redefine existence. But in every case, one truth remains constant. 3i Atlas is now outbound. It has passed the Sun, survived what should have destroyed it, and continues on a trajectory no other interstellar object has followed. It's leaving, but it's leaving traces. Those traces are what November, December and March will measure, and when those results arrive, they will not only tell us what happened, they will tell us whether humanity has just observed the first deliberate act in space not performed by our own species. In the meantime, the world keeps watching, half with scientific rigour, half with disbelief. The night sky hasn't changed, but our understanding of it has. Somewhere above that horizon, invisible to the naked eye, a faint blue traveller drifts outward. Silent, stable, and just slightly off course. No message, no transmission, only motion, impossibly precise, mathematically defiant. And perhaps that's the message after all. When the first rumours of 3i Atlas began spreading months ago, it felt like another curiosity in the long archive of cosmic wonders, a rock from beyond, something to measure, catalogue and move on from. But what began as astronomy has turned into something else entirely, a mirror. Because the longer we've watched this object, the less we've learned about it, and the more we've uncovered about us. Our fears, our limits, our reflex to explain what doesn't fit. And now, as the data builds, fragments of numbers, incomplete images, silences that feel too organised to be chance, the meaning of this event is no longer confined to science. It's philosophical, existential, and deeply human. For generations, science has lived by a quiet assumption that every unknown is temporary, that with time, the universe yields. But 3i Atlas has reminded us that some mysteries aren't errors of measurement, they're signals of scale. Every parameter that defines it, its near-perfect ecliptic alignment, metallic chemistry, anomalous acceleration, improbable stability, seems designed to hover at the threshold of understanding. It's as though the universe has written a riddle that's solvable only if we learn to read differently. For now, we're still reading it like a comet, a rock, a machine, because those are the categories we have. But maybe this isn't about an object at all. Maybe it's about the edge of comprehension itself, a test of how far observation can go before meaning collapses. 3i Atlas has become a reminder that not every truth is meant to be immediately knowable. Some are meant to haunt the frontier, pulling our curiosity forward. The second meaning is psychological. In the absence of data, humanity projects. Some see technology, some see theology, some see deception. 3i Atlas has become a kind of Rorschach in space, a shape we fill with our own reflection. For scientists, it's the embodiment of doubt. For believers, it's a sign. For governments, it's a liability. For the public, it's proof that the universe is finally interesting again. It has revealed how quickly mystery destabilizes certainty and how fragile our definition of normal really is. If tomorrow NASA confirmed that 3I Atlas had changed course intentionally, the discovery would be seismic, but what would follow might be even more revealing. The struggle to name it, the hunger to categorize, the chaos of interpretation. Because humans don't just seek truth, we compete to own it. That's what this event has shown most clearly. The stars haven't changed. We have. When an interstellar object crosses into our solar system, it doesn't just cross distance. It crosses categories. It forces everything we thought was distinct to overlap. Physics becomes philosophy. Astronomy becomes theology. Observation becomes interpretation. If 3I Atlas turns out to be natural, then nature itself has become intelligent enough to mimic intention, and if it's not, then intelligence has become patient enough to mimic nature. Either way, the distinction breaks, that collapse, between what is alive and what merely behaves as though it were, may be the most significant conceptual shift since Copernicus. It moves the question of are we alone, away from life and toward agency. We used to think the universe was silent. What if it's not silent but subtle? What if its language isn't sound or signal but precision? 3. Atlas doesn't speak, it acts, and that action, if deliberate, is the oldest form of communication there is. The agencies are learning this lesson the hard way. The past month has exposed not only the limits of science, but the limits of how science is shared. When the blackout began, the public trusted the data. When the data stopped, they turned to speculation. And now, with partial leaks, conflicting statements, and coded language, trust itself has become the casualty. NASA and ESA didn't just face an anomaly, they faced a new category of event, one that is both physical and psychological. Managing information about an unknown isn't like managing a crisis, it's like managing faith. Every withheld image, every redacted line, every pending review amplified the silence until the silence became the story. In a way, that's what 3I Atlas exposed most clearly, the inability of human institutions to handle mystery. We want certainty. The universe offers ambiguity. And ambiguity, to bureaucracy, looks like danger. But in truth, ambiguity is the birthplace of discovery. At its core, this event asks a single question. What do we mean by intelligence? We define it as reaction, as purpose, as self-awareness. But what if intelligence can exist without consciousness? What if it can be written into motion, coded into trajectory, embedded in matter itself? If 3 Atlas is acting according to some logic, gravitational, magnetic, or designed, it challenges the anthropocentric idea that intelligence must look like us. Maybe intelligence is not thinking, maybe it's pattern, maybe it's order that persists against chaos. The philosopher Alfred North Whitehead once said, "The universe is the self-organizing process of experience." 3 Atlas might be the most literal expression of that idea we've ever seen. A process so perfectly organized that we mistake it for intent. But if intent and order are indistinguishable at this scale, then the universe itself may already be alive. Not conscious in the human sense, but aware enough to correct, to steer, to survive. Somewhere, right now, in a dark control room at ESA, a small group of scientists is staring at an incoming data stream, watching numbers that no one on Earth has ever seen before. They don't know yet whether those numbers will confirm the extraordinary or dissolve it, but they know that either way they are witnessing something that will never happen again. Because the first time humanity realizes that the universe can surprise it, truly surprise it, is the only time it can. Everything after that becomes adaptation. And that's what this moment is. A turning point not in what we know, but in how we know. It's the moment the cosmos stopped being background and started being active, responsive, unpredictable, maybe even aware. Whether 3I Atlas is a machine, a mineral, or a messenger doesn't matter yet. What matters is that it exists in the narrow space between comprehension and awe, and that for once we're humble enough to look and admit we don't know. If there's meaning in all of this, it's not encoded in a radio beam or carved into an artifact. It's written in motion, the oldest script of all. something entered our solar system, crossed behind our star, and came out different. That difference, however small, is the sentence, and it reads, "Change is possible." Perhaps that's all the universe ever wanted to say. When future generations look back on this month, the conjunction, the blackout, the return, they may not remember the technical details. They'll remember the feeling, the collective pause, the moment we all looked up, not out of fear, but out of recognition that something vast was moving with intent and that we were capable of noticing it. For centuries we've been asking the cosmos one question: is anyone else out there? 3. Atlas may not have answered in language we understand, but perhaps it did answer, just in physics instead of poetry. Because when an object from beyond the stars passes so close to our sun, endures its fire, and then changes course as if guided, it leaves us with no real conclusion, only continuity. And maybe that's the point. Maybe the universe isn't done teaching us. The story of 3i Atlas doesn't end here. It leaves us suspended between wonder and understanding, the same place where discovery truly begins. Soon, the next data will arrive, the next measurements, the next image, the next silence, and when it does, it will carry the weight of everything we feared and hoped might be true, that the universe is not empty and that its gaze has already met ours. The light has returned, the silence has broken, and yet we're left with something more unsettling than answers: continuity. 3i Atlas didn't end with a crash, or a flare, or a revelation. It ended with motion, still outbound, still stable, still just far enough beyond our reach to remind us what unknown truly means. Over the past month, we've watched the limits of certainty fold. Institutions designed to measure matter have found themselves measuring meaning instead. Scientists became philosophers, observers became participants, and data became narrative. But beneath all of it, beneath the theories, the fear, the silence, was one quiet truth. Something from beyond our star crossed into our sky and made us look up differently. Maybe 3i Atlas is just a coincidence written in metal and light. Maybe it's proof that we're not the only engineers in the dark. Either way, the event has done what discovery is supposed to do: remind us that the story of science isn't about knowing everything. It's about what happens next when we realize we don't. So as telescopes continue tracking that faint blue traveler disappearing into deep space, one fact remains unchanged. The universe is not static. It acts, it surprises, it waits. And somewhere out there, 3i Atlas keeps moving, past Jupiter's corridor, past the reach of our probes, carrying with it the silence of whatever secret it chose not to leave behind. For now, all we can do is follow, because if the cosmos has just begun to speak, the least we can do is listen.